today's morning session. And I'm Ekaterina Loktiva, a professor on the chair of physical chemistry here in the chemistry department of Moscow State University. And I will present for you two lectures on different topics. First lecture will be devoted to catalytic disposal of environmental micropollutants. And the second lecture will be about catalysis in transformation of biomass to chemicals and fuels. From these topics, you can see that I am catalyst chemist and I'm working in the field of heterogeneous catalysis. Let's start. Outline of my lecture is presented here. I will speak about the definition of micro and macro pollutants, the ways of its disposal, and about catalytic hydrodequination, which is my preferred topic. I'm studying catalytic hydrodequination in different ways. And after that, conclusion. First of all, about the definition. You know that a great variety of organic chemicals are developed each year. And so there are so many of organic chemicals that target analysis is performed only for limited number of such chemicals. You see here the pyramid, and only the top of pyramid is compounds regulated by law. Then there are compounds which are not regulated by law, and for them we can perform target analysis. And then there is the basement of this pyramid. This is unknown compounds, and they can be presented in the environment, and so for them we can perform only non-target analysis. Environmental micropollutants are synthetic or natural compounds that enter the environment from local and non-local sources in low concentrations. Usually they are located in the aquatic environment. However, some micropollutants can be found also in the ground, in soil, in air, and in other medium. Micropollutants are often not controlled or monitored, and therefore have adverse effect on human health and the aquatic world. And it is the important issue, and it is becoming more and more important during the last years and decades. Micropollutants include pharmaceuticals and personal care products, detergents, steroid hormones, industrial chemicals, pesticides, and other classes. Here is the border between micro and micropollutants. You can see the border is 1 microgram per liter. And so, sorry. For example, phosphorus is a macropollutant, not micropollutant. The same is for dissolved organic carbon and for nitrates. But heavy metals is on the border. They can be treated as micro and macro pollutants. But pharmaceuticals, bio and other pesticides, and endocrinic disruptors can be put into category of micropollutants. And the boxes here reflects the number of known pollutants of this nature. You can see here that inorganic metals, they are all in the table of Mendeleev, yes, periodic table. And it is limited number of metals which can serve as micro or macro pollutants. Organic pollutants are plenty of them. There are plenty of them, and it is more widespread. And microorganisms, you know that the greatest number of bioorganisms is microorganisms. So there's plenty of them, and so many of them that this box is the biggest one. Some words about classification of aquatic pollutants. I'm speaking mainly about micropollutants. Organic micropollutants can be divided to pharmaceuticals and personal care products, agricultural, including insecticides, pesticides, etc., endocrine disruptors, disinfection byproducts, micro and nanoplastics, plasticizers, organic dyes, and persistent organic pollutants. Organic dyes are often used in researches because it is very easy to find out if the organic dyes are disposed or not, because the color is changing. And what about persistent organic pollutants? Mainly it is chlorinated wastes. Chlorinated wastes, it is a majority of persistent organic pollutants. They are regulated by Stockholm Convention on persistent organic pollutants, and between them are very important and very dangerous substances. Some words about the danger of aquatic micropollutants. You know that increased production and consumption of medicine and lack of disposal strategies influence on our attitude to these class of pollutants. Can you raise your hand who is taking any medicine? Anyone? Nearly all of us here and there taking some medicines. And you see that when you are buying your medicine, you see the great and long list of adverse effects of this medicine. And you must understand that when metabolic process proceed in our organisms, then the rest of this medicine put into the environment. And the same will happens with human bodies after death. And so our environment became more and more polluted with these pharmaceuticals. The expected consumption of antibiotics in 230 compared to 215 is 200%. For thousands of new molecules, long-term effects are unknown and cocktail effects are possible. For example, endocrine disruption, bioaccumulation, biomagnification of exposure, antibiotic resistance, etc. Micropollutants, as I said before, are not taken into account in the rules and regulations for the environment. And household wastewater irrigation distributes micropollutants to the surface waters. It was special research in Australia, performed in Australia. You know that in Australia there is the lack of water, and they tried to use household water to irrigate vegetable gardens, and find out that this irrigation disseminate pollutants between the soil, and so after that the groundwater and drinking water became dirty. As my professional interest lies in the field of chlorinated chemistry, I know that chlorine-containing micropollutants are very widespread, and they are very dangerous because they are xenobiotics. They are not presented in the human body or animal body naturally. They are persistent organic pollutants, so they stay in the nature long time, and they are accumulated in food chains. Why? Because they are not hydrophilic, they are hydrophobic. And when you go from simple organism to complex organism, so it will be accumulated, and so the concentration in human body will be the highest, especially when you use, for example, fat fish. Uh, Micropollutant medicines are numerous. They are often found in water. I divided them into three categories. First of all, antibiotics and antibacterial agents. They are tetracycline, sulfamethoxazole, fluoroquinolone, triclosan. There are anti-inflammatory and cardiac agents, ibuprofen. Uh, I, I think that all of you know of ibuprofen. Carbamazepine, diclofenac, it's the object of my close interest, atenolol, diuretics and statins, furosemide, again, very popular medicine, hydrochlorothiazide, and benzoyl uh, pesticides, often also found in water, and you can see from their very popular mosquito repellent data. You can see here saprosid, chlorpyrifos, very popular insecticides, and also carbaryl. Is there anyone from India? No, from India, no. Uh, Carbaryl was the reason of great disaster in India, Bhopal tragedy. You know about Bhopal tragedy. It was the uh, chemical accident at the production of carbaryl. Endocrine disruptors. These are substances which in the structure, chemical structure, are very similar to hormones. And they may interfere with the hormonal system and produce harmful effects in both humans and wildlife. For example, you can see here bisphenol A, which is very popular co-monomer for production of polymers, and the structure of hormone. And you can see, as in this picture, mm, uh, they can make chemical connection with the receptors and hinder the action of hormones in human body. Disposal of micropollutants. Most conventional treatment plants, they often include coagulation, filtration, chlorination processes. They remove up to 50% of pharmaceuticals and are not designed to completely remove micropollutants at low concentration. So it is necessary to develop methods for their removal. These methods are developing, and they are numerous, and some of them summarized here. You can see here the most attractive method is adsorption because it's easy and cheap. But what we are doing when we adsorb micropollutants on the adsorbent? So we concentrate them, not dispose them. And then the problem of disposal stay again. There are biological methods. Biological methods are very attractive because it is the methods they are working in the nature. But usually they are very slow, and they are demanded huge installations to perform them because the concentration cannot be high, concentration is very low. There also are chemical methods. Can I ask you, you are a chemist or maybe ecologist? Who are you on profession? Ecologist, ecologist, geologist, yes, chemist, chemical engineer. Oh, nice to meet you here. So there are chemical methods which the most popular again are oxidation methods. Oxidation because it is easily to process any toxicant, any pollutant by incineration, by combustion. But for some reason, it is not so attractive as on the first glance. Because first of all, some of wastes are easy to incinerate. For example, it is so for chlorinated wastes. Chlorinated wastes are not so easy to combust, to burn. Again, oxidation is dangerous because very dangerous products can be formed, and I will talk about this later. There are also advanced oxidation processes, which are processes where the acting agent is hydroxyl radical. And this is Fenton process, electrochemical processes, and so on. There is also decomposition. For example, photochemical, electrochemical processes, often in the presence of catalysts. And there are membrane processes, for example, nanofiltration, reverse osmosis. And then there are reductive methods, for example, hydrodechlorination or dehydrochlorination. Here you can see the sketch presenting the variety of bacteria for processing of a variety of micropollutants. All bacteria are producing usually CO2 and water, especially if they are aerobic bacteria. But there are also the class of anaerobic bacteria and the classes of genetically modified bacteria, which are improved to process more hardly processable micropollutants. Some words about features of drugs disposal, medicines disposal. Medicines have strong physiological action, and medicines that easily degrade in nature are easily removed in bioreactors and activated sludge treatment plants, so unusual water treatment facilities. But there are other medicines which are very stable in the nature. For example, it is sotalol, nitrochlorothiazide, carbamazepine, macrolides. They can also not only be hardly removable, but they can interact easily with other drugs and can be made biodegradable by some type of treatment. And they are the class of very hardly disposable, biodegradable, persistent polar pollutants, such as diclofenac, mecapro, sulfur phenyl carboxylates, complex compounds such as ketoprofen or naproxen, and antidepressant fluoxetine. More efficient methods than biotransformation need to be applied for this class of medicines. For example, if you are ill, you can use paracetamol, and paracetamol is very easy degradable. But in some cases, you used instead diclofenac, and diclofenac stays in nature 1 year and 2 years, and then. Some words about these listed above methods. This is scheme of absorption of pharmaceuticals on multi-volt carbon nanotubes. You see that absorption, the most cheap absorbent is active carbon, but active carbon is a microporous material, and so many different new carbon materials are more attractive than active carbon, and in recent years they become enough cheap to be used as adsorbents. And you can see from here that the adsorption can be performed by donor-acceptor electron interaction, by hydrogen bonding and PIP hydrogen bonding, by Lewis acid-base interaction. So there are different types of interaction, and then by easy treatment, we can improve the absorption properties. For example, treatment by nitric acid provide us more and more nitrogen-containing defects when the pollutants can be absorbed easily. Hydrophobic interactions play a minimal role, and the effect of pH due to changes in polarity of groups in the adsorbate and carbon nanotube surface can play essential role. As I said before, the problem with adsorption methods is concentration but not removal of pollutants. It is necessary to develop methods for recycling adsorbents, or better, the regeneration. To solve this problem, it was proposed the use of nanocomposites, including an adsorbent and additional components, and it can have a complex effect. They can be used as sensor, adsorbents, and agents for decomposition of micropollutants. During absorption or after absorption under the influence of some conditions, maybe temperature, maybe radiation, maybe some other methods. In terms of cost and complexity of synthesis, nanocomposites are much inferior to activated carbons. For example, such complex action can be provided by photocatalysis. And some systems were proposed for the use for disposal of organic dyes. You see, I said that the activated carbon is microporous material, but graphene and graphene oxide is not so strictly defined by micropores, and they have this material has a very good and high specific surface, and they can be used for adsorption of pollutants, but in combination with semiconductor nanoparticles such as titanium, zinc oxide, cadmium sulfide was prized by Nobel Prize in this year. Yes, for the photocatalytic decomposition of dyes. Also, instead of these very simple systems, another metal oxides can be used. For example, iron oxide and complex oxide of manganese, iron, and so on. How the photoregeneration of the adsorbent is performed? By irradiation with visible light. You see that adsorption capacity of such composite porous aerogels, graphene, triazine frame, and PVA, adsorption capacity is about 2,000 micromole per gram of tetrahydroxybenzophenone. Self-regeneration was achieved, it was close to 90% for the fourth cycle. So it can be cycled again and again and again. And regeneration by, again, close to 90% after 7 days of operation. The role of graphene or graphene oxide is adsorption. The role of triazine framework is regeneration due to photocatalytic properties. And PVA organized the porous system of such composite, removal of stacks from 2D structures, and the chemical bond between graphene and triazine. And you can see from here that 3 composites were prepared with medium, short, and long binding PVR length chains. And you can see the comparison, and in each cycle, the best was provided by medium chain length of the PVR chain. No, here you can see the abstract from this article, and you can see the adsorption capacity, regeneration capacity, and also UV filter. UV filter is this substance which is processed by this composite. Membranes. As I said, the membranic methods are also widely used. For example, membrane based on metal organic framework named ZIF8 and on titanium oxide was used for methylene blue removal. Also, here was used polysodium styrene sulfonate. And you can see here the way of self-assembly of this composite and the transforming of methylene blue. And here you can see also the membrane made of this nanocomposite, the scanning electron images, and the structure of this membrane. A Fenton process is very usual oxidative process. And here you can see the scheme and dependence, or later dependence on pH of the solution. You can see that here is the pair iron 2 plus, iron 3 plus, hydrogen peroxide, which produces in redox processes hydroxyl radical, which as a hammer break down the pollutants on the smaller molecules. And here you can see the dependence on pH, and you can see here that only a small interval of pH is appropriate for processing such micropollutants. Because in other pH intervals, you have no this appropriate electronic pair. Homogeneous Fenton process is limited by pH and high consumption and loss of reagent, and it is very expensive. So it was developed the heterogeneous Fenton processes, which can work in wide pH range with a recycle of reagent. And many Fenton-like processes, advanced oxidation processes, which used not only iron pair, but also metallic iron, copper pair, pyrite, etc. Process can be activated by irradiation, cavitation, electric field, and other influences. Especially attractive is the use of iron, nanoparticles of metallic iron, because a reaction can be performed on the surface, reducing iron losses. The addition of copper deepens the processing of amoxicillin due to alloy formation. Generation of hydrogen peroxide in situ, for example, in this scheme of EDTA, iron 3 plus, is very attractive, and this region is named green region. Also, stabilization of iron particles can be performed using carbon shell, clay, Nafion resins, zeolite, cotton, etc. Process based on golden redox pair also is very attractive. And this pair was deposited on nanodiamond, which is produced during utilization of bomb and other explosives. Here you can see the composite composed of palladium, the pair of iron and iron oxide, and multi-walled carbon nanotubes for cleaning of water from 2,4-dichlorophenols with magnetic separation. The presence of iron made it easily to separate this composite after the decomposition of micropollutant by ordinary magnets. And combination of adsorption capacity with hydrodechlorination made this method complex and very, very effective for catalytic dechlorination. There is also interesting topic of nanomotors. A biological decomposition of pollutants can be performed in water and also the mixture. You see that processing of mixture usually is much more difficult than the processing of one single micropollutant because of hindering action of different micropollutants. Nanomotors or micromotors are active colloids that can move independently in liquids to perform complex tasks. Enzymes are excellent candidates for motor in nanomotors due to their biocompatibility and excellent catalytic properties. And here is the example for lactase, which is an enzyme from the class of oxidases containing 3 copper atoms, and it is environmental friendly. Nanomotors based on lactase supported on composite comprising the iron oxide core and silica gel shell have been proposed. Pollutants serve as fuel for nanomotors. What pollutants? Bisphenol A and Congo red. The composition of such micropollutants close to 100% was achieved in 40 minutes. You can see here the preparation method for such nanocomposite. And here you can see the photo, microphoto, and you can see that the particles have dimensions of about 10 micrometers. And what we can see from catalytic results, here is black bars is free lacase, and here is lacase motor, so moving lacase moving in the solution. And you can see that free lacase deactivates fast, but lacase used as nanomotors have nearly no deactivation during time. You can see here days of the use, 60 days and nearly no deactivation of this motor. And you can see from here that not only single micropollutants can be disposed, but also the mixture of bisphenol A and Congo red can be easily deactivated. Some words about my topic, the disposal of diclofenac. It was shown in the literature that it can be performed using Fenton-like processes on iron catalysts. But here in this article was used interesting catalytic system where iron was reduced from salt by sodium borohydride, but palladium was recovered from the salt using bacteria. And you can see the name of this bacteria, Enterococcus fecalis. So it is used intestine bacteria, usual for each human body. And you can see here the structure of this nanocomposite and the reaction which proceeds generating hydroxyl radical. Pathways for converting diclofenac in oxidative reaction are very different, various. And you can see that many of products can be formed, and between them partly chlorinated, and destruction goes deeper and deeper to form many products. And at the end, thermodynamically stable CO2, water, and chlorine ion. Disposal efficiency is high, about 100, close to 100% for 20 and 40 minutes for the use of fresh particles of such composite. But disadvantages of oxidative processes of diclofenac processing are presented here. First of all, ozonation. If you use ozone as oxidizing agent, so the formation of toxic diclofenac 2,5-aminoquinone and 5-hydroxydiclofenac is expected. Oxidation with aqueous chlorine dioxide leads to the formation of very toxic oxychlorine derivatives in small quantities, but we are speaking about microtoxicants. So in small quantities, they are still toxic. Advanced oxidation processes based on pulsed radiolysis leads to complete removal of diclofenac, but reduction in ecotoxicity is only 40%. Only small reduction in ecotoxicity due to the formation of toxic byproducts. Similar effect was found in other advanced oxidation processes, such as photocatalysis, UV-activated persulfate, photo-induced catalytic wet peroxide oxidation. So in this case, very attractive are reductive processes, such as hydrodeclination. You can see here the scheme of diclofenac hydrodechlorination. You can see from here that a wide range of chlorinated xenobiotics can be processed by hydrodechlorination. That reduced toxicity is achieved by removing chlorine and other halogens. You can see here maximum permissible concentration of diclofenac, and it is much lower than maximum permissible concentration of this final product of hydrodechlorination. And the same is valid also for chlorophenol, which is also micropollutant. The maximal permission concentration in this case is very low, in this case much higher. We performed experiments on hydrodeclination of chlorophenol and diclofenac in water, in batch reactors and in flow-type reactors, and with preliminary reduction of catalyst in different conditions. And what we find out that usually palladium is reduced at 300 or more Celsius degrees to reduce more palladium. But we performed interesting and very scrupulous study by photoelectron spectroscopy and find out that very efficient reduction of palladium can be achieved at as low temperature as 30 Celsius degrees. So at room temperature, nearly at room temperature, we can nearly totally reduce palladium and so save the environment by using much less energy for reduction of palladium particles. You can see here the performance of palladium catalysts in the first run and second run. First run is without reduction, second run is with the reduction. And you can see that the performance of catalyst by reduction much improved. You started from 7% and go to 100% of conversion. And we also find out that the reduction of catalyst can be much improved also by modifying of palladium catalyst by iron oxides. Iron oxides are a very good modifier to improve the reduction of palladium, and reduction can be achieved faster and more totally than in the absence of iron oxides. You can see from here the results of XPS studies for unreduced palladium, unreduced catalyst, for example. Here you can see 100% of palladium in oxidized state. When we reduced at 320 Celsius degrees, 100% of palladium is metallic. But when we used 30 Celsius degrees, also we can see half of palladium is reduced. For some catalysts, more than half palladium is reduced. But the problem which we find out also by this method is that the palladium in not modified catalyst go to the bulk of the catalyst, go from the surface to the bulk. You can see here the theoretical aluminum palladium ratio. Aluminum is from the support, and real aluminum palladium ratio. And for example, in not modified catalyst, it is started from 200 and goes to 1,000. So all palladium is going into the bulk, and it is not, the reagent cannot be adsorbed on palladium because palladium is hidden in the bulk of the catalyst. And you can see very good results. So during 10 minutes, we have nearly total reduction of diclofenac. Do you remember I mentioned for some composites, it was 20 or 40 minutes for such total transformation. Here is very good catalytic way. And it is hydrodeclination in flow system. You can see here the volume of past diclofenac solution, and you can see very stable catalysts which are working and working and working and can be used in flow type system. For example, in the work of Brazil scientists, the membrane reactor for such purpose was proposed, and they also find out that catalyst palladium supported on alumina is working very long time. Conclusion of my speech. The problem of the presence of micropollutants in the aquatic environment and other environments is underestimated and requires analysis. Drug disposal systems and improved water treatment systems are needed. Especially they are needed in those places where the micropollutants are formed. For example, on industries where medicines are produced, in hospitals. And here is the problem of mixed micropollutants, because in hospital you will have the mixture of many medicines of different nature. And so the method of their processing must be efficient for all of them, or at least for majority of them. And also it is necessary to develop inexpensive, effective, stable, and regenerable adsorbents and catalysts for the processes of safe disposal of micropollutants under flow conditions. Thank you for your attention. Have you any questions about micropollutants? No. So, in this case, да. Так, как это делать? Рабочий стол, как показать? Вот, да, сейчас. Да. Там две, по-моему. А посмотрите, снизу две связки. Ага. All of you, raise the hands who know what is green chemistry. One, only one. Two. So during my speech, I will mention green chemistry, but first of all, I must to say for you that green chemistry, in contrast with brown chemistry, is aimed on not producing wastes. There is, for example, ecological catalysis when you produce waste and then transform them into safe substances. For example, all of you know that catalysts are equipped with catalytic neutralizer, yes, which process CO, nitrogen oxide, and hydrocarbons to safe chemicals, CO2, water, and nitrogen. But in this case, we first create wastes, and then we are processing them. And it is not very attractive way, especially from industrial point of view. Why? Because imagine you are a businessman, you are producing some chemical, and you must to buy raw material for your chemical, yes? And after that, you process your raw material into product. And imagine the yield of reaction is not 100% and yield is 50%. So 50% of raw materials you bought to produce wastes. You produce wastes for your account. And so green chemistry, when you don't produce waste, is very, very profitable for businessmen. So it's very good and interesting approach aimed on high selectivity, high yields, reducing of steps of chemical reaction, because you know pharmaceuticals are produced in very long ways. Yes, you need 10 or maybe more reaction steps to produce very fine chemicals such as isomers, optical isomers, yes. And if you find a way to produce them not in 10 steps, but to perform this reaction in one step, you will have great economy for your purse, and you will have a great economy for environment, because the amount of waste will be very much diminished. And this is concerning biomass. The outline of my speech is here. I will speak about chemicals from oil and from biomass, biorefinery, lignocellulose fractionation, features of heterogeneous catalytic transformation of biomass, plant oil to motor fuels and lignin to motor fuels, and future trends in this field. And first of all, I searched through Science Direct. You all use Science Direct in your research work, about the number of publications on keywords catalysis plus biomass. And you can see from here the exponential growth of such publications from 1995 to present time. And you can see also that for one chemical from biomass, 5-hydroxymethyl furfural, the number of publications each year now is about 1,000 papers. So it is the topic of great research interest. And let us compare it with the scheme changing of price for petroleum Brent. You can see here the rise and the decrease and then the rise. And let us compare these two these two curves. And you can see that the interest to catalysis and transformation of biomass is following the trends for Brent oil. So it is very closely connected values. Let us compare biomass and oil reserves. Worldwide biomass production is about 2,000 billion tons per year. And total proven oil reserves is about 250 billion tons per year for production per year. In both areas, Russia is between the leaders. You can see that Russia having 21% of world biomass each year, and Russia have 6% of total proven oil reserves. Not first place, but closely after Venezuela. Let us compare production of chemical and fuels from biomass and from oil. First of all, oil. This process have many advantages and disadvantages. Advantages are full industrial integration. The petrochemistry was developed since the end of 19th century. So it is very well developed area with very good and efficient processes. It's solvent-free processing with low E factor. Who knows what is E factor? E factor. E factor is environmental factor. Environmental factor. It was developed by Roger Sheldon in Delft University, and the formula is presented here. It is the sum of moles of side products or waste to the number of moles of desired product. So E factor demonstrated us if you're producing 1 kilogram of desired product, how many kilogram of waste you produce. For example, if the E factor is 50, how many kilograms of waste you produce per 1 kilogram of desired product? How many? E factor is 50. 50 kilograms. And it's real numbers. It's real numbers for pharmaceutical production and fine chemicals. Green chemistry is defined through the 12 principles of green chemistry. And one principle of green chemistry is a raw material or feedstock should be renewable rather than depleting whenever technically and economically practical. So if we compare oil and biomass, only renewable resource can be used only in the case when it is economically practicable. Otherwise, you cannot use the biomass because it's very expensive. So we can see here that a low E factor is characteristic for all production of chemicals and fuels from oil. Why? Because many catalytic processes are used in such production. Nearly all petrochemical processes are catalytic. For example, cracking, hydrocracking, reforming, and other processes of oil transformation. Also, oil and products for oil have high energy density and well-established logistic. It's very important. But there are drawbacks. It is exhaustible and it provides carbon emission. Carbon emission is the great issue, and it is the reason of anthropogenic climate changes, which we see around us each year. About biomass. Biomass also has some advantages and many disadvantages. Advantages that biomass is renewable and sustainable and carbon neutral, because when tree grows, it takes carbon for this growth from CO2 from the air. But drawbacks are partial industrial utilization. You see that biomass has different composition. In contrast to oil, oil is composed of hydrocarbons. So the composition of hydrocarbons is hydrogen and carbon only. Some other additives, but in very small amounts. But biomass is composed from hydrogen, carbon, and what element? Oxygen. So when we deal with biomass, we need the processes of deoxygenation. Deoxygenation to remove oxygen and go to hydrocarbons as traditional fuels. Or we must perform the processes directed to produce something combustible, something giving energy, but comprising oxygen. Conversion of biomass often is performed in solvent, at least at aqueous media. So high E factors are characteristic for biomass transformation. And it has lower energy density than oil and very difficult logistics. You see, for example, you are producing ethanol from crops or maybe better, not from crops, but for the wastes of production crops. Yeah. So your business must work the whole year, but biomass is growing not the whole year. For example, in Russia, only in summer. So in summer, you must produce the raw material for the whole year, and you need to have a place to save this amount, huge amount of biomass for your industry working smoothly the whole year. So the logistic is very, very important issue in transformation of biomass. Let's see what chemicals are we usually producing from fossil resources. Fossil resources are oil, gas, and air. Air, not fossil reserve, but air is using in transformations. Not a very great number of chemicals. First of all, it's BTX fraction, benzene, toluene, xylene, and buthanes. Also, ethane, ethylene, and syngas, CO plus hydrogen, ammonia, methanol, and hydrocarbon fuels. And from this limited number of base products, we are producing another chemicals: styrene, adipic acid, caprolactam, phenol, acetone, terephthalic acid, ethylene glycol, and so on. And this is all, nearly all, what we need to produce polymers, our paints, our clothes, and other demanded materials. But when we are starting from biomass we can produce starch, cellulose, hemicellulose, lignin, plant oil, and in addition, proteins when we are using animal biomass. Animal biomass, for example, you use chicken, it's very fat, and fat from chicken you use in production oils and proteins. And from this, you can produce syngas, as here, syngas. You can produce sugars, glucose, fructose, xylose, starch, arabinose, lactose, sucrose, organic acids, polymers, extraction products, and from these substances, you can further, by catalytic way, produce all these listed chemicals. So this way, joining, we can produce all substances which are now producing from fossil oil from biomass, but the processes are often much complex. So here is biorefinery concept when we produce biomass utilizing CO2 and water from the environment, and then from this wood biomass we produce all chemicals what we need, and in such production catalysis plays a major role. Why? Catalysis, it is another principle of green chemistry. Catalysis, catalytic reagents, as selective as possible, are superior to stoichiometric reagents because, as I said before, all your wastes you are producing by yourself. Yes, in reaction, when we use, for example, stoichiometric changing reaction, so you produce the waste. Catalytic reactions are attractive for three crucial reasons. First, high reaction rate. It is in the definition of catalysis. Catalysis is the increasing of reaction rate. Second reason is energy saving, because catalyst, why it is increasing the speed, the rate of the reaction? By decreasing the activation energy. Decreasing the activation energy, it means saving of energy. And third, you know that when we are producing energy, we are producing wastes usually, yes? And then high selectivity. High selectivity can be achieved in catalysis by different ways. For example, by usual common catalysts, zeolites, it is achieved by the presence of ordered porous system. For example, when you are methylating of toluene, you can produce different xylols, but only xylenes, but only paraxylene can enter from the channel, and so the selectivity to paraxylene will be very high. So 3 strategies using catalysis were developed to produce chemicals from biomass. First strategy is through decomposition to low molecular weight molecules. You are process biomass by high temperature processes, for example, pyrolysis, gasification, and then produce syngas. Usually syngas from biomass is different in composition from the syngas from oil because it comprises more CO2. And then by catalytic ways, you produce from syngas hydrocarbons and alcohol. For example, by Fischer-Tropsch synthesis, very well known and very well developed process. You see that here we are close to oil chemistry because from oil we also produce CO2, syngas, and then hydrocarbons and alcohols. So here we can use the existing facilities. We produce syngas from biomass, and then it went to the petrochemical facility and transformed there. But there are other ways to transform biomass. It is very attractive, but it demands very much energy because it's high temperature processes, pyrolysis, gasification, it's very demanded on energy processes. So what you are doing when you process biomass in this way, you are by hammer breaking all the bonds between elements, and then you become new huge work on collecting substances from these many little rests. But the biomass is plant polymers. You have huge parts of molecules, and if you are careful, you can save these parts in the pool and use them to construct the needed desired chemicals more mildly. And this is another way through base molecules or platform molecules. It is biorefining concept. When you use part of biomass to produce energy and another part to break bonds, but not so totally. Close bonds between some monomers and produce platform molecules, and then by catalyst ways to produce base chemicals. And here you can see, you can expect also 2 ways, because these base chemicals may be close to those which we are producing from oil. For example, you can produce terephthalic acid and then polyethylene terephthalate. Each of you have a bottle with water made from polyethylene terephthalate. Yes, but you can produce another substances, for example, furan dicarbonic acid, which are substituting terephthalic acid. It's a different acid, but also with 2 carboxylic groups. And it also can be used to produce polymers with different properties. And you see, both approaches are attractive. But as for now, the most attractive is to produce those base chemical which we are now producing from the oil. But for the future, another approach will be more attractive, to produce different chemicals of different structure, new products which can substitute the oil chemistry. And then there is direct transformation to products, so-called one-pot synthesis, which is also very attractive. And one example is production of biodiesel from vegetable oils. You know that biodiesel is produced from vegetable oil in a esterification process, also catalytic process. And the definition of platform chemicals, renewable carbohydrate-derived building blocks, providing the basis of the sustainable chemical industry of the 21st century, for the production of fuels, chemicals, and materials. Then I will shortly comment on these different types of biomass processing with the mentioning of new interesting processes which are developed recently. For example, cascade catalysis. Cascade catalysis means that you are performing several transformations in one process. For example, I told about gasification of biomass to synthetic gas. Gasification in the presence of water can be performed, but there are several problems connected with this process. First, soot and resins in products. Second, the activation of catalyst due to coking in these unstable conditions. Low yield of syngas, usually about 60%. High content of CO2 due to reactions with water. And low quality of syngas due to complex products composition. So expensive cleaning is needed for this syngas. Possible solution of this problem is two-stage process when pyrolysis is joined with reforming. It will help to increase the stability of reforming catalyst because it is not used on the stage of pyrolysis. Independent temperature control for each processes and increase yield of biochar, which can be used to obtain valuable products. And here you can see the scheme of this product. First of all, by pyrolysis, we produce biochar, and which is used for pre-reforming of biomass gasification products on biochar. And then the reforming was performed on nickel, which is formed by reduction of nickel aluminate to produce syngas. And from this syngas, biofuels, biomolecules, biochemicals. The advantages of this process is deep destruction of large oxygenate molecules due to significant contact time with biochar. After generation of water vapor, and for reforming, improved yield and purity of syngas. Yield is about 90% compared with 60% in this old process, and stability of nickel catalyst, which are not coked, which is not deactivated. You see that processing of biomass can be performed as a whole, but often biomass is first fractionate to produce, for example, lignin, cellulose, and hemicellulose. And from these components, lignin is the least valuable. The most valuable are cellulose because paper is produced from the cellulose, but lignin is a little bit of waste. And the processes to process lignin to produce something valuable are very, very demanding. For example, peroxide oxidation of native lignin. In this catalytic process, cellulose-soluble products from lignin and hemicellulose can be produced. Also, anaerobic oxidation of native and technical lignins on copper catalyst can lead to aromatic aldehydes and cellulose. And these are works of Russian group of chemists, which are placed in Krasnoyarsk region. You know where is Krasnoyarsk? Krasnoyarsk city is in the middle of Siberia. It's an interesting city. And the school of Professor Kuznetsov is working on this development of these methods. The most active catalyst for peroxide fractionation of wood is titanium oxide. It is cheap and eco-friendly. Its counterparts are sulfuric acid, which is corrosive and toxic, or molybdenum oxide and complex molybdenum oxides, which are very expensive. Liquid phase catalytic processing of soluble lignin into valuable chemical process can be performed on alumisilicates, on carbons, or on ruthenium modified carbons or alumisilicates. And you can see that when we are modifying these catalysts with ruthenium, the composition on products changes. Without ruthenium, we have mainly coke and liquid products, and little amount of gaseous products. And when we are adding ruthenium, here we have mainly liquid products, so hydrocarbons, it's very attractive, more gaseous products, and nearly no coke. For example, when we are using as a support ZSM5 zeolite or sibonite. Sibonite is another interesting carbon material. It was developed in Boreskov Institute of Catalysis, situated in Novosibirsk. It is very, very good carbon support, comprising pyrocarbon on the soot. And what are the products of such transformation? They are a little bit different for sibonite and ruthenium on sibonite. And you can see from here that are phenolic compounds and some alkaline chain substituted phenolic compounds. What chemicals can be produced from the components of wood biomass? As I said before, components of wood biomass is cellulose, hemicellulose, and lignin. From glucose, cellulose, we can, by hydrolysis, transform it to glucose and produce nearly all variety of hydrocarbons starting from C1 and to C6 valuable products. And C1 includes methane, formic acid, syngas, and C6 includes sorbitol, fructose, mannitol, 5-hydroxymethyl furfural, and many intermediate products. Hemicellulose, by hydrolysis, we can transform to xylose, and by hydrogenation and deoxygenation, we can produce gamma-valerolactone, tetrahydrofurfural, pentoic acid, 1-pentanol, and the most interesting is the ways of transformation of lignin. By CO cleavage, we can produce monomers, glycols, phenol monomers, and then by hydrogenation and deoxygenation, alcohols and hydrocarbons. Very interesting concept was developed naming lignin first. Before fractionation of biomass, you can destruct the lignin to produce some monomers of lignin, and then perform fractionation of biomass. It was performed by oxidative catalytic fractionation with hydrogen peroxide, with oxygen, by reductive catalytic fractionation, but acid catalyzed fractionation with stabilization of alpha and gamma hydroxyl side groups in the form of acetals with formaldehyde. Monomer yield is close to theoretical. Then some words about platform molecules. For example, from cellulose, you can go to glucose and produce platform chemicals. Here is presented the use of glucose as platform molecules. You can see here that many ways includes fermentation. By fermentation, you can process glucose to produce different organic acid, muconic acid, hydropropionic acid, and so on. Also, you can join fermentation with oxidation or to perform hydrogenation, oxidation, dehydration. And all of these processes are catalytic, including fermentation, because fermentation is made by enzymic catalysts. And the key products here are organic acid, which are by itself platform molecules, and also 5-hydroxymethyl furfural and 2,5-furan dicarboxylic acid. I told you about furan dicarboxylic acid, which can substitute terephthalic acid, which is produced in oil chemistry. This is substitution from biomass way, sorry. And 5-hydroxymethylfurfural is very, very attractive platform molecule. And there is a very interesting paper by a famous Russian chemist, Valentina Anannikov, about 5-hydroxymethylfurfural as sleeping giant of biomass processing. Because when we waken up this sleeping giant, it can be used in different ways to produce very interesting chemicals. Here is the ways of the use of this sleeping giant. Selective oxidation, aldol condensation, hydrogenation with ring cleavage, esterification, selective hydrogenation, rehydration, and all of these products are demanded, and especially demanded, for example, 2,5-dimethylfuran, because by itself, hydroxymethylfurfural was attractive to use as a fuel, but it is not stable. It is polymerized easily because it comprised three functional centers: aldehyde group, furanic ring, and hydroxymethyl group. So it is polymerizing, and it needs to be stored in very, very low concentration solutions or in very, very clean state as a crystal substance, crystal solid substance. But 2,5-dimethylfuran is very stable, and it is has very high energy capacity, comparable with those of hydrocarbons. So it can be used as fuel by itself, and it can be mixed with other fuels, hydrocarbon fuels. So it is treated as the candidate from biochemistry, chemistry of biomass, for substitution of hydrocarbon fuels. And you can see here many other interesting, valuable chemical products. Here is furfural as a platform molecule. Also, you can see that maleic acid, furoic acid, and other products can be produced, including butane and long-chain alkanes, which are now producing from oil. Heterogeneous catalysis is the most attractive type of catalysis in substitution for homogeneous catalysis. Because when we are talking about transformation of biomass, we must use mainly acid-base catalysts, and usual homogeneous acid catalyst is inorganic acids. For example, sulfuric acid, phosphorus acid, and it is very corrosive, it is very aggressive. So advantages of heterogeneous processes is easy separation of catalysts from products, lower corrosive properties, easy regeneration, more convenient control of catalyst properties due to the availability of wider range of reaction conditions. And especially important is possibility of multifunctional catalysis. Because when you are going to perform cascade or tandem reactions, you need different active center in one catalyst. But when we talk about homogeneous acid, you cannot add the base active center to acid because it will neutralize. But in the solid catalyst, you can join the acid and base center in one catalyst and add redox center, for example, metal, and other to produce multifunctional catalyst. The features of catalytic biomass transformation. First, solid surface of biomass, solid surface of catalyst, and non-homogeneous composition of biomass. It is a very specific and very much touching feature of biomass, because the composition is changing, and so the product composition and yields of product will change with the composition of biomass. Its topochemical nature of biomass transformation. Topochemistry is reactions involving solids localized on the moving outer boundary of the solid reactant and reaction product. Different availability of components. Amorphous lignin and, for example, crystalline cellulose. It's different components, and it has different availability for catalysts and reagents. Impossibility of using many industrial catalysts due to deactivation in aqueous media. For example, many industrial acid catalysts is for example, zirconium oxide modified by CO4 groups from sulfuric acid. But when you add water in your medium, it will dissolve in water and acidity will decrease. Strong influence of mass transfer parameters is observed, and this complicates the use of heterogeneous catalysts. So here you can see the picture presenting the variants of interaction of biomass with the heterogeneous catalyst. Catalyst on the surface of biomass, dissolved or molten catalyst on the surface of biomass, and mixed biomass with catalyst, and a fixed or fluidized bed of catalyst. You know, fluidized bed, it's very attractive way to perform catalytic reaction. Interesting methods were developed. There are types of transformation with indirect catalytic action, where catalyst generate an active intermediate in reaction medium, and then it goes to plant polymer and transform it to organic polymer. Indirect catalytic pathways simplify the technology by providing possibility for the use of fixed or fluidized bed of heterogeneous catalysts for processing plant biomass. What catalysts are demanded? They need to have high activity towards heterogeneous raw material. They need to have porous structure with large pore sizes because biomolecules often are large, and they have need to have stability in aggressive aquatic air environments. For example, it can be oxides of zirconium, titanium, niobium, carbon. Zeolites are not so attractive because of microporous system, but now the science in the field of zeolites going to add to them mesoporosity, to make them micro-mesoporous materials instead of simply microporous materials. So many mesoporous materials were developed, such as MCM41, CBA15, and so on. For example, my magister students now this month was preparing 2 types of SBA15 modified by zirconium. Novel carbon materials to substitute microporous active carbons, for example, graphene, nanotubes, etc. Here is the graph presented the processing of plant biomass into more convenient energy carriers. You can see that you can simply press biomass to produce pellets or briquettes with low energy content. You can see you can perform hydrolysis or fermentation to produce bioethanol and biobutanol. Our previous country, United USSR, was the first developing many processes of bioethanol and biobutanol production from biomass. And then extraction and esterification we will come to biodiesel. From thermal dissolution, we come to liquid fuels. By gasification, we will go to gas fuel and liquid fuels by Fischer-Tropsch synthesis. And by pyrolysis, we can produce bio-oil, biogas, and coke. Some words about generations of fuels. First generation is made from edible biomass, and it is not so attractive because it may diminish the food chains. Second generation is made from non-edible biomass, from wood, straw, grass, waste. Third generation from algae, microalgae, microalgae. And fourth generation, it's different breakthrough technologies. What fuels when we made from biomass? It can be oxygenated fuels, and the most common types of oxygenated fuels are ethanol and and fatty acid methyl ethers, often abbreviated by FAME. Biodiesel is made by esterification of triglycerides of fatty acids. Catalyst is sodium methylate, and ethanol is usually produced by fermentation of biomass, preferably of second or third generation, to ethanol by enzymatic catalysis. These are good fuels, but there are some obstacles preventing their wide use. You know, in what countries ethanol is widely used as a fuel? Brazil first and USA. In Brazil from the sugar cane, and in USA from corn biomass. Yes, and in Brazil even there is the technology of a flexible fuel or motors for vehicles in Brazil are adapted to work on the mixtures of ethanol with ordinary fuel. And in Brazil, ethanol is used in not very dry state, but in USA, ethanol first is drying until the 100% purity. But more appropriate is the use of hydrocarbons produced from biomass. It is known as the green gasoline, green aviation fuel. Composition is the same as in common counterparts from the oil, but only the source is different, biomass instead of oil. And there are several catalytic methods of bio-oil refining to liquid hydrocarbon fuels, and they include hydrodeoxygenation, catenization, zeolite upgrading. And side products are synthesis gas, and main product, desired product is liquid hydrocarbon fuels. And hydrodeoxygenation of fatty acid of triglyceride has some features, and it can be performed as one-stage or two-stage processes. And two-stage process is the example of tandem reaction, which includes hydrolysis of vegetable oil to produce free fatty acid, and then hydrogenation and hydrodeoxygenation of them, and separation of raw diesel from the excess of hydrogen. You see from here that in production of free fatty acid, we go to glycerin. Glycerin is not demanded product because in production of biodiesel and such fuels, it can be very dirty, not of a good quality. But in this one-stage process, instead of glycerin, you will produce a propane. Propane is much more attractive as glycerin and much more demanded product to produce, for example, propylene, and then from propylene the polymers. I will not go to this, but you see that lignin, which is the waste from production of cellulose, can be depolymerized to phenolic intermediate, and then by hydrodeoxygenation or selective hydrogenolysis transform to natural fuel additives, aromatic fuel additives, oxygenates as fuel additives. I know at least two industrial technology of production of hydrocarbon fuels from biomass. First was developed by Neste in Finland, and it is direct catalytic hydrodeoxygenation of vegetable oils into the corresponding alkanes and propane. The glycerin chain of triglyceride is hydrogenated to propane. There is no byproduct production of glycerol, and catalytic isomerization is then carried out into branched alkanes to adjust cloud point and meet winter performance requirement. Unlike first generation biodiesel, this diesel contains only hydrocarbons. Since it is chemically identical to ideal conventional diesel fuel, it does not require any modifications or special precautions to the engine. And another technology is made by Halder Topsy. Halder Topsy is Dutch company, which is well known in Russia because in previous years it provided grants for postgraduate students in Russia, very good grants. It includes the stipendium 300 euros per month and attendance of their facility. Very interesting stipendium. In this firm developed the hydroflex technology, also catalytic hydrodeoxygenation to process nearly any renewable to fuels on demand. Interesting feature of both technologies is that they can work on different raw materials depending on the customer. They will adapt the technology for your need and to produce naphtha, jet fuel, diesel in different amounts, again, according to your desire. This is the table from the presentation of Halder Topse, which demonstrate the difference between diesel produced by Hydroflex technology and first generation FAME diesel. Cetan number is much higher, clot fluidity is much higher, mixability with other oil fuels here is up to 100%, here is very limited. And market value, therefore, is very high. Here is comparison of these two processes, not comparison, but presenting the facilities. Two oil refineries in Finland, two larger refineries in Singapore and Rotterdam. They first used palm oil. It is a different joke, interesting joke, because Finland created this facility to use own raw material. Own raw material in Finland is wood sawdust, maybe wood material, but they used first up to 90% of palm oil. Palm is not growing in Finland. And then they're moving to more appropriate raw materials, and now the share of palm oil dropped less than 20%. And for Halder Topsy technology, there is constructing the facility in Brazil with a capacity of many tons per year, planned to launch at the near future. I will not speak about this because I have no time. And future perspective. Petroleum refining was developed since the end of 19th century. It is expected that biorefinery will develop into high-performance industry in 21st century. New generation of highly stable, active, and selective solid catalysts to convert polysaccharides and lignin to valuable products are highly demanded. And here is the field for the activity of young scientists. A multifunctional heterogeneous catalyst can transform biomass and its components in one-pot synthesis, cascade, and tandem reactions. Reducing of the number of stages opens the way for resource and energy economy in transformation of the main components of lignocellulose biomass into wide assortment of base chemicals, products, and fuels. Thank you again for your kind attention. Have you any question on this part? So if you will have question, you will ask your authorities and they will give you my email and you can write me. Thank you for your attention.
Алло, меня слышно? Что-нибудь скажите, чтобы мы поняли, что звук идет. Так, вот у вас звук выключен. О, вот теперь
Так,
включен.
я вас слышу хорошо, да?
Так, вот и вас тоже слышно. Так, у вас там все нас видно, слышно? Все нормально?
Да, все в порядке. Могу включать демонстрацию экрана, да, уже?
Да, давайте включайте. Все?
Хорошо. Так я на английском говорю,
Да, да,
да?
да, да.
Окей. Well, welcome to my talk. I would like to let me. Ну, здесь у меня организатор отключил демонстрацию экрана участников. Включите, пожалуйста, демонстрацию экрана. Окей.
Да, появился.
Okay, maybe I will just show in this format because otherwise you may only see the first picture, not the others. Okay, let us try. Okay, today I'm going to talk about catalytic processes that can be used for utilization of diverse carbon-rich wastes and some products of their processing. And let me start with methane, though methane is not considered usually as a waste or as a some very cheap product because usually it takes quite some energy to convert methane into something valuable. So I will start with microwave activation in the catalytic processes, and the microwave is standing alone among many other methods of activation. And all we know that usually microwave quants possess very low energy, so they cannot break the bonds, chemical bonds. They can only cause fast movement of molecules and therefore very significant heating of the material from the inside. But we can use microwave or plasma for catalytic processes via either in situ activation of the processes or ex situ via the preliminary activation of the catalysts. Here I collected some advantages of microwave heating. First, fast heating is very important, otherwise we lose a part of heating, a part of energy, and we will create some gradients. Fast heating allows to reach very high temperature within a few seconds or 1 minute. Fast cooling is also very important because in some cases, especially in the case of partial oxidation processes, the products of such processes are very reactive and we need to cool them very quickly in order to prevent their further unnecessary conversion into undesirable products. A principally different mechanism of heating allows to heat selectively the material inside the reactor without heating the reactor itself and carrier gases or sometimes even solvents. Enhancement of dispersion and activity I will demonstrate in using specific examples. In some cases also we can enhance the selectivity of the process by creating some non-equilibrium conditions. So let me briefly focus on three mechanisms of microwave heating. Dipole polarization is well known because we use this mechanism of heating when we heat the food or water. And this is realized via the presence of dipoles in the heating mass. Well, this mechanism is well realized when we work with polar groups, polar molecules. But when we work with non-polar species like hydrocarbons or asphaltenes or lignin, the heating is very poor. Therefore, we need to use conductivity mechanism or Maxwell-Wagner mechanism, which include the heating of semiconductive or conductive materials, or selective heating at the interfaces of different phases present in the system. This is Maxwell-Wagner effect. So let me demonstrate a few examples. For instance, when we use a very simple catalyst like nickel wires, meshes, we can convert selectively methane with a very high conversion to acetylene or a mixture of aromatic molecules. So basically, acetylene is the main product, and about 30% of the mixture is a composition containing benzene, toluene, and xylenes. But this process occurs under very severe conditions. So the formal temperature is above 700 degrees C. Nevertheless, we can compare different types of plasmas. Here you can see the comparison. And spark plasma or direct barrier discharge or corona plasma can provide quite efficient conversion of methane with reduced spending of the energy for molecule. And this is the example of the microwave plasma. So we see here that the benzene concentration in the mixture is not very high, reaching 0.6, 0.7%, and the average power is quite significant. The methane conversion may reach up to 40-45%. And you see that not very high energy expenses are reachable under moderate conversion of methane. But as I already mentioned, the main process is formation of acetylene. So, as I mentioned already, the activity and selectivity enhancement are the main advantages of the microwave, selective heating of microwave. And we can compare different materials in the catalytic processes. Some of them require large energy input because they are insulators like alumina. Titanium dioxide is a little bit better because it is semiconductive material, and carbon is the best one because it is a conductive material, and the energy input here you see that is about 200 times smaller as compared with platinum and alumina, for instance. The presence of hydrocarbons or hydrogen in the mixture causes the reduction of the input energy, but we will not dwell upon this effect in this talk today. We also try to measure determine the rational parameters of the microwave activation, the density of power and the strength of the electromagnetic field. And again, you see the same trend here. The strength is much higher as compared with carbon-based materials. And while the density of power is, the difference is not that much distinctive as compared with the strengths. The methane conversion under microwave or microwave plasma conditions can provide unsaturated molecules like acetylene or ethylene, synthesis gas, carbon black, aromatics, or CO2 if we wish to just burn methane. And here the table illustrating the oxidative coupling of methane to produce C2 hydrocarbons. You see the main products are ethane and ethylene. And the conversion reaches 20-25%, and the microwave activation provides the reduction of the reaction temperature by about 200 degrees C as compared with the thermal activation, whereas the product distribution is about the same. You see that the diverse rare earth metal oxide compositions are used and are efficient in this process. The same reaction and about the same catalyst. And again, you see that the microwave mode of activation provides the gain in the reaction temperature, and in some cases the gain of the conversion. However, the yield of ethylene is a little bit reduced under these conditions due to the thermodynamics of the process. If we want to convert methane into synthesis gas, again, we should use supported metal catalysts like cobalt or nickel, and comparison of the microwave with the thermal heating shows that there is a gain of the conversion, and in some cases selectivity, especially for nickel-based catalyst. And you see that usually thermal heating provides the low conversion as compared with microwave heating. And the yield of carbon monoxide is higher in the case of the microwave heating. Now we should switch to CO2 processing. CO2 is a main exhaust of power plants or cars, should be somehow utilized into valuable products, and we consider mostly conversion of CO to synthesis gas, or CO2 to synthesis gas, or to hydrocarbons or methanol. And this is an example of dry reforming. So here we use two gases, methane and carbon dioxide, to convert them jointly into synthesis gas. Here we can use nickel-based compositions. It is important to know that under thermal conditions, the fast deactivation occurs in this process because the temperature is usually very high, reaching about 900 degrees C, and coke is formed under these conditions. So within 5-6 hours, the catalyst loses about 2 times in its activity. But if we, at this point, switch the mode from thermal to microwave for both catalysts, we will see immediately the regeneration of the catalyst. So in some cases, it almost reaches the initial level of the activity. Noteworthy that under microwave heating, we remove the major part of coke accumulated during the thermal process. So about 25% of coke is accumulated for fluorided nickel alumina catalyst. And about 2/3 of this amount is removed during the microwave heating. Now, we are trying to use not only microwave for these catalytic processes, but also supercritical conditions, and mostly catalysts containing no noble metals. And the target products include not only synthesis gas like carbon monoxide and hydrogen, but also methanol, hydrocarbons, carbonates. In some cases, some oxygenates are also possible. And we are trying to synthesize all of these compounds. So this is the general scheme of the reactions. Well, I would say that methane is not a useless product. In some cases, when you have some extra energy, for instance, in the peak times during the night, you can produce methane from CO2 by using this extra energy. So we, in addition to the old tricks like formation, synthesis of organic carbonates or salicylic acid or urea or soda, we can produce also methane, olefins, alcohols, produce carboxylated species, and more complex organic compounds. Just a few examples of the use of supercritical carbon dioxide as a reaction media and as a reactant itself. So you see that under supercritical conditions, the CO2 reduction occurs with a high conversion, reaching 35%, and the catalyst is quite stable. Well, but depending on the catalyst, we produce mainly, well, in the case of ruthenium, for instance, mainly methane is formed, whereas in other cases, we produce a mixture of carbon monoxide and methanol. Like in the case of iron on alumina, very simple, very cheap catalyst. The conversion reaches 22%, and the selectivity to CO and hydrocarbons may reach totally about 80% or more. So this is my favorite example of the use of supercritical conditions for methanol synthesis from carbon dioxide. And you see that the conversion may reach 40% under very mild conditions at about 300 degrees C. So these are different catalysts containing copper, zinc, and some other additives. And you see that the performance is quite different depending on the composition. But in most cases, the selectivity to methanol is very high, reaching 100% or 98%, with a few exceptions at higher temperatures. So the productivity of the catalyst may reach in the peak position up to 3 grams of methanol per gram of the catalyst per hour. And I must say that this value is about 10 times higher as compared with the subcritical processes, which are well reported in the literature. So you see that the pressure influences the conversion and selectivity. So this is a very low temperature of the reaction, therefore the conversion is not very high, but the selectivity is quite high. And the productivity here reaches 1.3, which is about 10 times higher as compared with the best literature data obtained under subcritical conditions, so at about 20-30 atmospheres. And this value was found at about 75 or 80 atmospheres. Also, we can demonstrate under supercritical conditions the suppression of the catalyst deactivation. So during the process, simultaneous removal of condensation products occurs on the catalyst. Well, I have more examples of the use of microwave effects in CO2 conversion. And this is these are two reactions, CO2 reduction into methane and CO2 reduction into CO. And here we use 4 catalysts, which can be heated very efficiently by the microwave. So I must say again that not every catalyst can be very easily heated by microwave. For instance, if we take silica or alumina-based catalysts, they are heated very slowly and insignificantly. So here we used the materials which are heated up to 500 degrees very easily under very mild conditions. I mean the input power and the conversion may reach 90%, like in the case of this intermetallite. However, in this case, mostly methane was formed, whereas in these other cases, basically carbon monoxide was found in the products. So you see that very simple decomposition, very simple catalysts can be efficiently used for carbon dioxide conversion and utilization. So under microwave conditions, we studied methanol synthesis, as I already demonstrated, and CO2 hydrogenation to carbon monoxide and methanol. And the effects observed are basically enhancement of the conversion, decrease of the reaction temperature, and increase of the selectivity to target products. Also, in some cases, we observe a reduction of the extent of catalyst deactivation. Sorry, I am talking mostly about the results obtained in my laboratories, and I must say that there are interesting data from the literature, but because of the lack of time, I will just show the best of our results and in order to demonstrate how it works in practice. Synthesis of carbonates. So the process was realized under supercritical conditions. Here we can utilize 2 molecules, carbon dioxide and glycerol. Glycerol is also a very cheap product of biodiesel production, or transalkylation of glycerides produced from vegetable oil. So it is very cheap, and it doesn't find a large practical application. So we can produce by using these 2 molecules, which are very cheap, and this is a product with a negative price actually, because you have to pay in order to release carbon dioxide into atmosphere. We can produce organic carbonates like this one. Usually the literature data are very poor. I mean, the yields reported in the literature are below 2%, which is dictated by the thermodynamics of the process. So the theoretical yield is about 3% because of the very high, very unbeneficial thermodynamics of the process. So if we take a very simple catalyst, this is tin oxide on alumina, and will modify this catalyst was a little bit of copper, zinc, potassium, and boron. Then we can enhance the yield from 3% to about 18%, while keeping the selectivity at the level of about 98%. So this is a very important step forward in order to increase this, the efficiency of the catalysts under supercritical conditions. One more example of the use of carbon dioxide is carboxylation of acetylenic molecules. This is a very simple reaction occurring at almost room temperature in the liquid phase. So we just purge carbon dioxide through the mixture of a solvent and acetylenic molecule. Here we used phenylacetylene, for instance. And silver or copper nanoparticles are usually active in this process. So you see that silver nanoparticles, even present in a very low concentration on the support, provide a quite high yield of the propiolic, functionalized propiolic acid under 60 atmospheres. A very similar reaction. Again, we have acetylenic molecule, but we have here a functional group, which may interfere and block the reaction. But it didn't, because there is a CO2 interaction with the terminal proton in the acetylenic, which weakly acidic acetylenic molecule. And again, we produce the derivative of the carboxylic acid. The yield is not very high, but the selectivity can be enhanced to 95%. This is one more example, and it was obtained jointly with academician Beletskaya. These are copper nanoparticles, and you see that the yield may be as high as 97%, with copper nanoparticles supported on an appropriate support, and the functionalized acetylenes can be converted into these products. One more reaction of utilization of carbon dioxide is alkane conversion into olefins. Here we can see the scheme of the reaction, and we are aiming at propylene, but carbon monoxide produced here is also a valuable product. And you see that the conversion may reach up to 50%, but at a high temperature. And the selectivity to, sorry, this is propylene, not propane. So the selectivity may reach 90–95%, depending on the catalyst and depending on the temperature range. But mostly chromium-based compositions are used for this process, although gallium is also not much worse as compared with chromium. So these two metals are considered most interesting and most important for direct conversion of propane and butane into corresponding olefins. Maybe a few words about supercritical fluids and CO2. Once I have started to talk about supercritical fluids, we need to exceed the critical temperature and critical pressure, or one of them at least. And you see that carbon dioxide is very good from this point. That's it's very easy to heat CO2 and make pressure up to 75 or 80 atmospheres to improve the conditions to convert them into supercriticals. And You see that many other molecules also are good for this application, like hydrocarbons, nitrous oxide, other hydrocarbons, heavier hydrocarbons, but they need higher temperatures. Well, unlike this part of the list, water is not very favorable because it requires very high pressure, over 220 atmospheres, as well as ammonia, over 130 degrees C and 110 atmospheres pressure, whereas many others are still very good. I can skip this. This is quite general. One more example of the use of supercritical CO2 for conversion into formic acid. This is an example of the literature data, not our data, but we have reproduced these results and are trying to improve the catalyst. And you see that the activity, this is turnover number, the activity under supercritical conditions in the mixture of carbon dioxide with methanol is much better as compared with other solvents like supercritical carbon dioxide or methanol itself, or a mixture of supercritical CO2 with water or with dimethyl sulfoxide. So this is the best composition of the reaction mixture, which provides very high activity. But this is for a homogeneous complex. Now we are trying to make it heterogeneous. So again, enhancement of the productivity and suppression of the deactivation under supercritical conditions. Also, it's possible to have a kind of a tandem reactions in one pot. So this is an example showing how we can convert CO2 directly into propionaldehyde. Here at the first stage, we produce carbon monoxide, and then we do the reaction of formylation to produce linear normal propionaldehyde. And for this purpose, we use metal organic framework containing two groups of atoms: cobalt for CO formation and rhodium for formylation. And, and you see that the yield of propionic aldehyde may reach about 18% in the at moderate temperature, about 200 to 130 degrees C. And afterward, after reaching this temperature, side reactions predominate in the mixture, so we produce mostly undesirable products. But this system is very nice, and here we have a bifunctional mechanism, which is well illustrated by this tandem reaction. Another example is again the combination of cobalt in two reactions. Here again, formation of carbon monoxide, and then Fischer-Tropsch synthesis from carbon monoxide produced at the first stage, and the CO2 conversion is not very high, but a little bit better as compared with conventional cobalt alumina catalyst, and the activity is about 1.5 times higher, and the selectivity is a little bit better, selectivity to liquid products. So this is one example, and this is another example. Again, we on the same cobalt catalyst, we can produce again aldehydes with the yield up to 30%. One more example. Then here we have another catalyst, zinc and copper containing SAP35, silica aluminum phosphate, which is good, as known from the literature, for direct conversion of methanol to olefins. So we used this material as a support, and zinc and copper catalyze the reaction of carbon dioxide hydrogenation to produce methanol. Then methanol is converted directly to olefins, and the problem is that these two reactions need different temperature ranges. Therefore, we need to find a compromise between these two reactions. So the compromise provides the conversion up to 23%, and the yield of olefins only 21%, with the predominance of ethylene in the mixture. Usually, well, depending on the temperature in this second reaction, by using only the SAPO34 material, you can produce either ethylene or predominantly propylene by playing with the temperature and other conditions. Now I can switch to more heavier products from CO2 and methane. And here I will show some examples of the conversion of carbohydrates like cellulose and lignin, which is much more difficult case, and also some vegetable oils which are within this piece of the pie. So you know that the amount of biomass is enormous, so much larger than the amount of oil produced worldwide. So we can consider this material as a source of energy and chemical products. So in general, renewables conversion include conversion of, as I already mentioned previously, with the example of CO2 and carbonates, glycerol conversion produced from vegetable oil, which can be either converted to propane-diols or propanol, or oxidized into acrylics. Also, we can perform reforming of polyalcohols, including glycerol, sorbitol, in general cellulose, to produce synthesis gas. Transalkylation of triglycerides, then other reactions. I will show you some examples. I like very much ethanolysis of vegetable oil. I will not that much talk about this reaction, but just imagine you have a double bond in the middle of the long hydrocarbon chain in the maleic acid, for instance. Oleates like the seventh position of the carboxylic acid. So you can use ethylene to kiss the bond, double bond. So you produce two smaller pieces, which can be already used for production of diesel or maybe gasoline. So I will start with glycerol, and it is a platform chemical, and usually it is converted into valuable products by alkylation or acylation. So the market is huge, and the cost is extremely low, $100 per ton. And now we can go to plastics via lactic acid, for instance, or we can go to plastics via diols like 1,3 or 1,2 propylene diols. So in this case, we can produce terephthalates, and here we can produce biodegradable polylactates. As I mentioned already, we can also produce alkylates, which can be used as additives to the fuel, or acylates, which can be used as emulsifiers or other additives. Also, we can produce acrylic acid or acrylonitrile downstairs, and then synthesis gas very easy is produced from glycerol. These are literature data about the conversion of glycerol into, or propanediol into appropriate carboxylic acids. And you see that gold-based nanoparticles are used here. And we also tried to play with this with different alcohols, starting from ethanol and glycerol, and found conditions and very low-loaded gold catalyst, but still loaded with platinum, and found the conditions for the conversion of these two products into lactic acid, which is very valuable product. At the first stage, glycerol is converted into propanediol, so we can stop at this stage and produce, for instance, with the yield up to 80%, we can produce propanediol, which is also a very valuable product. You see the conditions are very mild. However, the catalysts still contain a large amount of noble metals. This is not a very easy task. And then this is a direct conversion. So we can, as I mentioned, we can stop at the stage of propanediol, but we can go further to either glycolic acid or lactic acid. So this is lactic acid, this is glycolic acid. They are formed as sodium salts because we use an alkali in the mixture. And you see that the selectivity to lactic acid is pretty good, about 64%. Here we use platinum catalysts on Syria, zirconia-based catalysts under rather mild conditions. The atmospheric pressure, no pressure at all, 60 degrees C, but we have to use sodium hydroxide or carbonate, but in this case the yield is and the conversion is very low. Gold-based catalysts are much better as compared with pure platinum. So improvement of the platinum catalyst with addition of gold results in the milder conditions and higher conversion of glycerol, 80%. So we can also use this bimetallic catalyst. So as we see, the turnover frequency is quite high, and the selectivity to lactic acid is about 60% or 62% in this case. Well, in some cases, actually, our Russian industry needs this process. For instance, we can convert glycerol directly to propanol or isopropanol or mixture of these two. The conversion is very high, 100%, and the yield of this mixture is about 94% because the rest 6% is ethanol, also not bad. The conditions are, well, appropriate, not very severe. That's temperature 250, pressure is about 30 atmospheres, and we use a quite concentrated solution of glycerol and water. And alkylation, this is an example of alkylation. This is a zeolite-based catalyst, which provides the best performance. The conversion is about 90%. Now I switch to higher alcohols, sorbitol and xylitol, C6 alcohols, polyalcohols. And we tried to convert them into, they are hydrogen rich, therefore we tried to convert them into hydrogen synthesis gas or into mixture of hydrogen and CO2 with downstream removal of carbon dioxide by using appropriate absorbent. So this is the overall scheme of the reaction. So this was proposed by Jim Demesic, and we tried to find a better catalyst for this process. So this is already our data, and here we used either gold or platinum catalyst or mixture of these two. And you see that the yield of hydrogen reaches about 70%. It decreases with increasing space velocity, but this is a very high yield of hydrogen taking into account the easiness of the separation of CO2. Here you can see the comparison of sorbitol and xylitol. In general, the dependencies look very similar, but there is a shift to higher space velocity in the case of sorbitol, and also some decrease of the selectivity with respect to hydrogen in the case of the sorbitol. So xylitol is a little bit better as a substrate. But in general, the conversion 100% is reachable under quite mild conditions of the process. So now we can switch to cellulose. Cellulose can be quite easily converted under microwave conditions. 1 hour, and you have glucose, and you can also have a kind of C6 polyalcohols, and the catalyst is very simple. This is a carboxylated or sulfonated carbon-based material. Also, we can use ionic liquids possessing acidic properties. And this is one example of the conversion of vegetable oil and similar products like oleic acid and stearic acid. And you see that the model catalyst, zeolite-based catalyst, provide a mixture of all the products. Well, each of these bullet includes many products, like about 10 compounds in aromatics, about 5-6 in the naphthenics molecules, and a lot of paraffins and olefins and isomers. Totally about 40 compounds in this mixture. But you see that by choosing appropriate substrate, we can produce either isoparaffins or aromatic molecules, depending on what we like. Triglycerides can be directly converted on modified ZSM5 or containing nickel or molybdenum into this about the same mixture. But the lighter products are formed here, light olefins and some oxygenated alcohols mostly. Well, these are more difficult tasks. How we can convert lignin or low quality coal like brown coal or turf or asphaltenes or hydrons and maybe solid municipal wastes or polymeric wastes into valuable products. I will show a few examples, a few pictures from the work of my colleague, Dr. Victor Bogdan and his colleagues. He tried to convert lignin into valuable products. And you know that lignin is not a very clear composition of polymeric units which are linked together, but usually they contain aromatic building blocks with C3 side chains and also some other carboxylated species in the composition. So by playing with the conditions and the catalyst, we can break either one bond or another bond in this polymer mixture, and also sometimes this bond. But the reactivities of these different bonds are, of course, quite different. So we can have a very large distribution of products depending on the nature of the substrate and the nature of the catalyst if we use the catalyst, and depending on the process conditions. So basically, ether links are more reactive. So this is the relative reactivity of the links. So ether bonds are more reactive. Then CC links are much less active, but depending on the source of the lignin, you see some variations in the distribution of the reactivities and products. That typically hardwood lignin has more ether links as compared with softwood lignin. So basically, even if we compare ether groups, alpha ether groups are more reactive than beta ether groups, and beta aryl groups are more reactive than aryl-aryl bonds, which are the least active in this composition. So lignin under these supercritical water conditions can be depolymerized mainly by cleavage of the ether links to produce mostly phenolic compounds. If more severe conditions are used, then it is possible to obtain a solid residue, not that much, and mostly hydrogen and carbon dioxide. So among the phenolic molecules, we can see, vanillinic acid, guaiacol, eugenol, and catechol, and many others. So this is just the largest product in terms of the yield. Then elemental analysis shows that some of lignin species contain also sulfur and nitrogen, so this is a more difficult task to convert such lignin. So these are lignosulfonate and kraft lignin, and which have different composition. I already mentioned that under microwave conditions, cellulose can be easily converted by using solid acid catalyst dispersed in the ionic liquid. Very easy process occurring within a few minutes with the yield of glucose reaching about 40%. So complete depolymerization of cellulose to produce glucose, the only product. Well, let us switch to dry reforming. So we take lignin, we take carbon dioxide, and we take iron precursor. Actually, we don't need a catalyst. We just add iron nitrate, for instance, into lignin mixture and plus carbon dioxide through this material. And you see that CO2 conversion. So our aim is to enhance the CO2 conversion and lignin conversion. So the CO2 conversion may reach 100%, but at a very high temperature, about 900. And anyway, you see that additives of iron or nickel or copper or cobalt improve the performance, and the conversion increases about 1.5 times as compared with pure lignin conversion. And the mixture of hydrogen, methane, and CO2 is formed. That you see that the concentration of these products changes depending on the reaction temperature. So if we need methane or hydrogen, we need higher temperatures for producing hydrogen as compared with carbon monoxide. Carbon monoxide concentration decreases gradually with increasing temperature. I must say that, as I mentioned already, iron or nickel species are most active when added to lignin as catalyst precursors. You can observe burning of lignin in the presence of carbon dioxide flow. That's the mass of lignin reduces to a very small amount of solid residue, which contains some inorganic species or coke, and in general, and also residue contains, of course, iron and nickel species, which can be again used with the next portion of lignin to produce hydrogen and carbon monoxide. Well, lignin can be converted into synthesis gas, but by a different approach. So here we use again microwave, and the reaction temperature is not quite high, about not higher than 200 degrees C. And we use here mixed oxide catalyst, which I can mention can be heated very efficiently to very high temperature, like 600 degrees C. So actually, this is a catalyst for a different process. This is a catalyst for ethane conversion into ethylene by oxidative dehydrogenation. But we use this catalyst for synthesis gas production. So you see that the composition of the gas mixture at the outlet of the reactor contains mostly, so we have used inert gas, of course, mostly hydrogen and mixture of CO and CO2. Then the conversion of oxygen may reach 95%. So we use a flow. This is air containing 25% of oxygen. And you see that the mixture of the synthesis gas is very poor. It's not exactly what we need for methanol synthesis, for instance, but it can be used for methanol, for production of ammonia, and after separation for methanol as well. Well, selectivity to hydrogen is about 60%. As I mentioned, the temperature of the reaction can be decreased to 150 degrees C, and the productivity increases about 2 times compared with the system without a catalyst. But without a catalyst, the process occurs at much higher temperature. Then, therefore, we have the energy consumption reduced by about 60% compared to the thermal process. But we can also produce phenolic molecules and hydrocarbons by converting lignin via hydrocracking on a platinum catalyst. So we used a platinum on carbon catalyst for mixed with lignin. So we have the solid material containing a catalyst and lignin, and then we passed hydrogen flow through this mixture and obtained a very complex mixture at lignin conversion. So we studied 2 samples. One of them was prepared by precipitation, another one was prepared by adsorption of platinum precursors. And you see that this one is much more active. And we produce a mixture containing hydrocarbons, C6-C8, about half of the mixture. Then phenol, ethyl benzene, other aromatics, and other phenols like these 2, and also some unidentified products. The amount of these unidentified products, more heavier products, is increasing in the case of the second sample. Again, the temperature of the reaction can be decreased to about 120 degrees C, very low temperature for hydrocracking. And again, we decrease the energy consumption for the process as compared with the thermal process. I guess this may be the last slide. And here, this is, of course, a model reaction. We can use turf or a model brown coal or plastic wastes for this process. So this is a kind of illustration how we can convert carbon containing materials like municipal wastes into carbon monoxide selectively. Further, carbon monoxide can be used for chemical processes. We compared thermal and microwave processes, and you see that under microwave conditions, the 100%, almost 100% conversion is reached at about 200 degrees lower temperature as compared with the thermal process. This is the thermal process. And again, iron, much better than nickel and copper, is acting as a catalyst. Well, actually, copper even is much worse as compared with the pure carbon. So here we have no catalyst. While adding copper, we decrease the conversion. So only nickel and iron play the role of active catalysts in this reaction. Again, we can decrease the reaction temperature by using microwave by about 150 degrees C, and we can decrease the energy consumption. And I'm afraid I'm here close to the end of my talk. And the last example is related to conventional asphaltenes or hydrones or maybe other boxes and other products. So this is an example of asphaltene. Again, you see that it contains a lot of sulfur, a lot of nitrogen, and this is the bad news because these molecules usually deactivate most catalysts like platinum or even palladium catalysts. And in order to convert this pretty heavy stuff into light products, it is not an easy task to break all these bonds. For instance, in this case, we have 5 cycles, condensed cycles. So we have selectively break at least 2 bonds in order to produce something light. But anyway, we succeeded in producing a gasoline fraction, so sweet hydrocarbon mixture containing mostly C6-C9 hydrocarbons. By using very simple catalyst, you see that, well, actually, platinum palladium, which is the most expensive in this comparison, is not considered as a good option for the process. So this is a commercial catalyst actually. And by using cobalt or nickel nanoparticles supported on a very simple carrier alumina, we obtained about 90% yield of the gasoline fraction. So this is a very encouraging results, I would say. So we will continue to work with different combinations of the active metals and catalyst carriers with the particle size and with the microwave and maybe other process conditions in order to improve the performance. Actually, this is also a commercial catalyst. 65% nickel doesn't make any better as compared with 5% of cobalt and nickel in these laboratory samples. So you see that larger loading of the metal does not improve the catalyst, but even decrease the activity. And this is for comparison a homogeneous cobalt nanoparticles, which were just mixed with asphaltene, and this mixture was converted in the presence of hydrogen. Also not bad, but in this case, there is a problem of recovery of cobalt, homogeneous cobalt nanoparticles. So we abandoned this system and turned completely to the heterogeneous systems. So I guess I'm at the end of my talk, and now I would like to thank you for your attention, and I saved some time for some questions if you like. I cannot hear you. I cannot hear you.
Do you?
Yes, I can hear you. Thank you.
Okay. I've just asked our participants whether somebody would like to ask a question,
Sure.
but I don't see that anybody would like to.
Okay.
Am I right? Am I right? Thank you so much for giving us this lecture.
Thank you for giving
Thank
me a chance.
Bye-bye.
Bye. Take care.
Okay, but up to the 8% of these plastics belongs to the microplastics. And so we have another troubles. Initially, we thought that it is a good way because of we have some dissolution, destruction, and the destruction is good and so on and so on. But now we are talking about the microplastic problems and troubles. So initially, we have some main ideas for the degradation of plastic, which forced us to use the oceans for the dumping of this waste. So the first idea was following. If sometimes something is made from the plastic material, is buried in the ground, so microorganisms will break down into carbon dioxide and water. So we will have mineralization if we will use microorganisms coming from the soil. But products made of plastic material can be thrown away with the biodegradable garbage. Why? Because by using the biodegradable materials, the microorganisms can increase their growth and activity against some polymers. So by mixing all of them, we can organize some kind of provocation and acceleration of the soil microorganism for the destruction, not only of the biodegradable, but other kinds of plastic materials. But to stimulate the degradation of plastics in the soil, we need to add water. So the idea was following. It is necessary to add water and plastic to the soil and everything will be okay. But after that, some guys decided it is necessary to dig the soil, to put their plastics. So it will be better to put all this plastic directly into the water, into the ocean, with a lot of microorganisms. So let's do it by the end. Let's go by this way. Moreover, from the chemistry, we know that in presence of water, we can stimulate the degradation of different compounds. For example, we can use or disrupt the carbonyl bond, and in case of X is equal to oxygen, nitrogen, or sulfur, finally, we can have the appearance of such product, and one of which is acid. And we can destruct by this way esters, amide, and diesters. Good. So also in presence of water, we can have the destruction of many other polymers containing like carbonate, uretane, urea, amide, and anhydride as monomers inside of polymers. But I would like to draw attention to the fact that in all these cases, we will have appearance of acids. So in all these cases, we will have the decrease in pH. It means that those microorganisms, as well as their enzymes involved in such destruction, can be inactivated or inhibited by the decreasing in pH. And so the guys who decided to organize the dumping of plastics said, oh, it's good solution to use the ocean because in case of soil, we need each time to change a little bit pH to stimulate the microorganism. But in case of ocean, we have buffer system. So no problem, start to do that. But it appeared that we have actually in presence of water, not complete destruction, but erosion of the surface and the plastic materials by the water when it ingresses inside or penetrates inside the structure of these polymers. And actually, the degradation of polymers can be divided into four main steps. So first of all, water absorption. After that, decrease in mechanical properties of some plastic materials, decrease in molar mass, and after that only we will have weight loss. And the degradation in the presence of water of different polymers, we can put into this line depending on some polymers which we have inside of this polymer. But it appeared that we can have two different types of water ingression into the polymeric bulk. First one, so we have named surface erosion. It happens with polyesters and polyanhydrides. And I would like to draw your attention to the word polyesters, because a lot of different plastic polymers are directly polyesters. So in this case, we will have surface erosion, very slow, when we have the mass loss, which will go faster as compared to ingression of water into the plastic bulk. So that is the reason of appearance of microplastics. But in many other types, first of all, biodegradable plastics, we will have another mechanism of ingression of water inside of such bulk of polymers. Ingression of water will be faster as compared to faster into the bulk of these polymers compared to the surface interaction. And actually, even 10 years ago, when we observed such destruction of bottles, for example, in soil, we close our hands and consider that everything is good. And now we have degradation of these polymer bottles. But now we understand that finally we have not the complete bottle, which we can treat by pyrolysis or other methods, but we have microplastics. And that is good or not? It appeared that we have some troubles, because the microparticles are light particles, and so they can circulate it in atmosphere because we have some evaporation from the ocean. And so after that, we can have some precipitations with the rain or snow of these particles everywhere. And moreover, we can have some interaction of these microparticles coming from the plastic with the dust, mineral particles, because mineral particles can absorb or be like carriers of such microparticles, hydrophobic microparticles coming from the plastics, regular plastic waste. So, and the main idea, so microplastic pollution is not static. So it in some dynamic action and movement. So it is not possible to prevent the appearance of these microplastic particles outside, even in our place where we are now. So probably you know that time to time we have information coming from China, from Beijing, that they have smoke outside. And a year ago, the scientists in Beijing decided to investigate the content of the air during the period of smoke appearance. And so probably you also know the main reactions participate in the appearance of classic smoke. And so that is why, taking into account all these reactions, you can see them here, and also reactions happen during the photochemical smoke appearance. So the scientists check all these parameters. But I would like to draw your attention to the presence of this marker. So some kind of particles, microparticles. And so they studied the content of all these particles, and it appeared that is of organic matter in red color. And there are a lot of such particles in the smoke, in atmosphere. It means that directly all these participants are a main reason of appearance of the smoke. And you can see here the size of such particles. So the size is close to 200 nanometers. And it appeared that is plastic, but not microparticles, but nanoparticles. Why? How do you think? How do you think? Okay, I will put this question because it is very important. And this is a picture demonstrating the prognosis up to the 100 year with increase in the appearance of microplastic, first of all, in the ocean. But we understand now that we also can have same increase outside in atmosphere. And you can see here bottles and bags, a lot of them. Okay, so how do you think? What is the reason of so huge growth, which is expected now till this period of time? How do you think? What is the reason? So we will drink a lot of water directly from the bottles. We agree to reject of using. So what will be the reason? The reason is absolutely in another place, because when other scientists studied to investigate the content of the microparticles inside of ocean, it appeared that there are a lot of synthetic textiles. Textiles, not bottles. Absolutely, because look here. So car tires, city dust, road markings, so marine coatings, and so on. Where is the plastic pellets? Only here. So we keep in our mind that we need to reject in using plastic bottles and bags, but we use synthetic clothes. A lot of our clothes contains synthetic polymeric materials, and we use these textiles each day. Moreover, time to time we wash it with some detergents in washing machines. You agree? And we do not agree to reject in using of these materials and in washing them. So that is for you. Some abbreviation, please look through briefly, because now I would like to give you information, sorry for this table, but I like this table because it is interesting that there are a lot of different countries. And so it means that there are a lot of different information coming from these countries about the presence of different polymers in the water. And you can see the shape. It means the source of appearance of these microplastics. So fiber, 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 fiber. So it's absolutely right idea that we have troubles with our synthetic clothes. And it appeared that we can observe the accumulation of microplastics directly in the ocean in sediments. And the deeper we will go, no, so deeper like in soil, no more than 8.5 centimeter. So we will see the increase in the concentration of these synthetic materials. Moreover, it appeared that the accumulation of these microplastics in the ocean sediments is happening due to the stop of oxidation processes. It's clear. And the reason of dangerous effects of microparticles for us, because of it appeared that we can get these microparticles through the ingestion of all. Do you know about these bags with steel core? So inhalation and through the dermal form. And of course, it appeared that the problem is following. Some chlorinated plastic can release harmful chemicals. We understand that. And so generation of reactive oxygen species, we will certainly observed in our body, in our cells, and not only in our cells, but in many others living organisms, including plants. And surfaces of these microplastics can contain and carry different disease-causing objects like viruses, microorganisms, pharmaceuticals, pesticides, prions, and so on and so on. So that is a real dangerous thing. But as concerning to the plant functionality, I need to say that we really have a lot of troubles because we can have the transpiration pool, and finally the microparticles can accumulate inside of the plant cells, and as a result of that, the appearance of information of such pigment like chlorophyll usually is reduced. And finally, we have the decrease in the photosynthesis. And some new idea coming from the literature, it appeared that even chlorella, so that is a microalgae, which can be added into the soil to increase the crops of some plants. So can lose, look here, like here, so, sorry, some cells without chlorophyll at all, because of the presence of microparticles around the cells. But it appeared that addition of humic acids into the soil can help us to a little bit improve the situation. So the conclusion is that for the soils which are contaminated by the microplastics, we can improve their state by adding humic compounds, because humic compounds can interact, absorb the plastics. And you can see also other sources where we can observe the accumulation of microplastic particles. First of all, in compost, in greenhouses, and in sludge coming from the enterprises treating the water. And another one source of the troubles with such type of textiles. Fictional landfills on the ocean coast in Africa as humanitarian aid, like gifts. Probably you do not know something about that, but I need to say that the fashion industry usually produce a lot of their goods, usually 4% percentage more than it could be bought. And after that, they collect all old versions of these goods and give like a gift to many African countries. For what? For decision of the problem of the treatment of and utilization of such waste. Because of if all these companies will pay for the utilization of already produced clothes, so they will pay for that. So they prefer to give such gifts. And that is a big problem, believe me. So it is possible to prevent somehow the appearance of micro and nanoparticles, plastic particles environment. If yes, what we can do now? So hypothetically, we can think of some filters or sorbents for ourselves and use them for each washing machine, to put into washing machine and to prevent the appearance of these micro plastic particles outside. But we need in good separation in each washing machine, not only at home, but in laundries and so on and so on. And we need in high velocity of flow, and we need in self-decontamination of such filters or probably sorbents and their possible regeneration and so on and so on. But it appeared that we can put some filters, and moreover, we use such filters for the preparing of drinking water for ourselves. And the result is following. Look here. So granulated activated carbon, powdered activated carbon, and ceramic filters. They do not work with such particles. That is a problem. But we have some imagination that we can protect ourselves by using this type of materials. No, only one procedure, reverse osmosis, can provide us the guarantee of separation of these plastics. But I need to say that reverse osmosis, that is a procedure which is used in Singapore, only in one country, for the preparation of drink water, only in one country. So actually, we use this procedure for the preparation of water in our laboratory instead of distillation, because probably you continue to use distillator for the preparation of distilled water and so. And Milicu also used, the company used same products to guarantee the obtaining of clean water for some chemical reactions, not only for the drinking, but in Singapore, it is the right way. And this is some kind of mechanism, but I will jump it over because I would like to show you another approach. Sometimes we have blockage and alcohol, and we try to use different solvents like purifying agent to fight with such a situation. And of course, we understand that we have some mixture of some waste, including microparticles inside of such trouble stopper. And we can try to use different types of such purifying agents, but it appeared that we can have only positive result with organic matter adsorbed on the surface of microplastics, but we have no any effect on the destruction of such plastic materials at room temperature, and even at the temperature a little bit higher. So that is a problem. But what we can do with the catalytic treatment of these materials? It appeared that in many cases, I repeat it again, we have polyesters. So probably we can use some enzymes which can hydrolyze the polyesters. So you understand that lipases are also esterases. And sometimes it is possible to think that we can use such regular enzyme to treat the bioplastics, or not bioplastics, but regular plastics with such enzymes. Believe me, we cannot do that because lipases have no chance to hydrolyze polymers. But if you will look through all enzymes which can be applied for the purposes of the destruction of polyester, you will see only two types of the enzymes. Usually we name it like polyethylene terephthalate and cutinase. That's all. And the problem, is following. We need, in addition of solvents, detergents, into such reactions with enzymes to improve the surface of their content, to enrich. And we need to increase the temperature to 60 Celsius degree. Sometimes it is necessary to use ultrasound for the pretreatment of these polymeric materials to give a chance of the contact of these microplastics with enzymes. And you can see that a lot of factors can influence on the result of such enzymatic treatment. But finally, we have some products, and we do not know what to do with these products because actually we need to introduce some special additional enzymes to destruct this product. Otherwise, we will have nano microplastic particles instead of microparticles. And that is a worsened situation. And application of different enzymes, you can see here, actually, directly at the beginning of this year, I forced my colleagues from my laboratory to analyze a huge volume of information. And we put the general results from 1,000 of different publications with the enzymes concerning the productivity of these enzymatic processes, temperature which we need, and pH. And it appeared that to apply some enzymes, we need in pH from 7 to 9. We need in the temperature close to 60 Celsius degree. And so for the environment, that is actually impossible thing. So it is not possible to wait the good biodegradation of such plastics outside. And so productivity is very low. Sorry about that. Moreover, it is necessary to organize or to provide the presence of enzymes on the surface of polymers to good bear their interaction. But enzymes are hydrophilic molecules, but plastics are hydrophobic molecules. So it is necessary to solve this problem. So we need in additions of detergents. Outside, it is not also good. So, and the main problems are following with enzymes. Sometimes we have, like our clothes, complex chemical content of these not bioplastic, but plastics. And so these polymer materials. So we need in the application of mixture of different enzymes, which will concurrently act with the polymers, which we have in some mixtures of such waste, which we would like to treat. But we need to add also a mixture or complex of different enzymes to provide step-by-step degradation of those polymers which are degraded. So conclusion, we need in complexes of enzymes. So we need in production of such enzymes. You understand? So who will do that? Because that is not a cheap solution. So much cheaper is collect some kinds of microparticles by using different sorbents and filters and so on and so on. And after that, treat all of these masses with some metal-containing catalysts. So actually, we come back to the pyrolysis, but with the application of some metal-containing catalysts. And so the question is, which type of the metal catalyst will be the best solution for such processes? Ruthenium is the best one. And sorry, I just jump here. One interesting solution which we discovered, salvolysis can be applied because the product yields, I mean, the product of degradation is high enough, the productivity is high enough, and the temperature of this process is low enough. And salvolysis can be conducted in the presence of acetone. But the conclusion is following. We need to solve the problem with the microplastic through the solution of production of polymer fiber materials, which we use in clothes, not with bags. So thank you for your attention. Since the next lecture will be also with me, sorry, that is the situation, as organizers ask me, I offer to you to have 2-3 minutes for the rest. No? Это дорого. Кто за это должен взяться? И самое главное, приводить в платье для того, чтобы постоянно обеспечивать себя. А что делать с тканями? Хороший вопрос. Ну, правильно, они считают это мусор. Нет, конечно, ну как? Вот нужно отделить, конечно, нужно отделить воск, да, который всегда присутствует. Нужно отделить, безусловно, вот этот сингаз. Ну, это решение есть, потому что оно вот пишет проще. Ну, вот этих процессов. Сингаз, он всегда образуется, и сепарация идет. Сейчас основное это то, что мы носим с вами синтетическую одежду. И больше ничего. И от этого мы с вами никогда не откажемся. А всякие бутылки, это все ерунда. Вот. Это ерунда. Одежда классная. И она каждый год обновляется. Новая мода, новая серия продукции и так далее. Куда девать старую? Нужно утилизировать. Ее не утилизируют, ее дарят. Гуманитарная акция. Окей. Let's continue. So, I need to say a few words concerning the mycotoxins because that is also a very serious problem, and we will talk a little bit about the possible solution. Because I would like to repeat that I'm a head of the laboratory of ecological biocatalysis. So first of all, I'm interested in the application of different biocatalysts like enzymes and cells in the solution of different ecological problems. And so today I will give you information concerning the mycotoxins. Probably you know something about that. So mica means fungal or mold or placing. And toxin means some kind of poison. And you already understand from the name of this toxin that all these toxins are absolutely natural and they are produced by fungal cells. And moreover, mycotoxins are considered to be components of the chemical defense system of fungi. Why? Because of, probably you also know, that as compared to different bacteria, fungi produce a lot of enzymes and secrete outside them to provide the destruction of different biopolymers, which they can use as a source of their nutrition outside of their body. And after they absorb already hydrolytic products for their functionality, metabolic activity, and so on. So to prevent the consumption of these hydrolytic products from other microorganisms, first of all, against the bacteria, the fungi produce antibiotics and mycotoxins. But we never name the mycotoxins like antibiotics because we use antibiotics for our purposes in the fighting of our fight against the bacteria, first of all. So we are talking about the mycotoxins, but concerning the synthesis of antibiotics and mycotoxins by fungi, sometimes we know the cases of allergy appeared after the acceptance of the fungal antibiotics like penicillins and cephalosporins and so on. And we consider that we have troubles with these antibiotics. But the idea is following. The antibiotics can contain some impurities like mycotoxins. And so the problems with the allergy can be not can be dealing not with the antibiotics themselves, but with the presence of these mycotoxin impurities. So some mycotoxins are also toxic for plants, not only for the microorganisms, but also for animals. I'm unsafe. So, and now we know we have the information about 4 100,000, not thousand, but 100 mycotoxins. And 2 days ago, I told you about the organophosphorus compound. And I compared these pesticides with chemical warfare agents. And I told a lot of, I told you this information about the chlorpyrifos. But now you can see at this information. So around the organophosphorus pesticide like chlorpyrifos, you can see here the mycotoxins synthesized by fungi naturally outside with different types of tolerable daily intake for each mycotoxin. And you can see that, for example, aflatoxin, citrinine, and so on, zearalenone, you can compare these amounts of these compounds, and you can understand that actually we have troubles because we have a lot of such mycotoxins or such toxins, which are more dangerous as compared chemical warfare agents. So what to do? First of all, we need to know about the dangerous situation with the mycotoxins which are around us, and to be very tentative to the situation. So cytotoxicity of mycotoxins. Mycotoxins, first of all, can modify the cell structures. I mean, they can stop the synthesis of proteins, DNA, and RNA. And moreover, the toxins can be stable after heating, after the treatment of strong acids, after the cooking, if we have the presence of mycotoxins in some food products. And moreover, due to the different structure of these mycotoxins, you understand that absolutely different structure you can observe. So it means that they can interact with different biological molecules inside of our cells, provoking different negative results and provoking the carcinogenic, mutagenic, genotoxic, immunotoxic effects. As well as in case of organophosphorus compounds, we can have cumulative effect also. And so the situation is following. We can get contamination of our agricultural crops by different types of the fungal cells during its growing on a field place. After that, during the transportation of already harvested, during the treatment and storage. But interesting fact is following. We can get this contamination, but in each case, the fungi which can do that will be different. For example, during the growth of some agricultural cultures or some agricultural crops, we can meet the contamination of different types of plants by the fusarium fungi. And they will produce some certain type of mycotoxin. So during the transportation and storage, we can get the contamination of the same plants or the same crops by other type of fungi. And they will synthesize and add into this biomass other type of mycotoxins. So finally, for example, when we can take some wheat for the production of bread or feeds for our animals, we can get the mixture of different types of mycotoxins in the same biomass. And that is the problem. And you can see here some samples. And time to time, we can get this situation, even with bread. And so what we usually do, we cut some piece and can eat up. No. So it's forbidden to cut into individual parts. It's forbidden because of the presence of these mycotoxins, of course, will be in the general mass where we can observe the presence of fungi. That is the main idea of their presence, because they would like to eat for themselves all this volume of some substrate. So they increase time to time the production of these mycotoxins. And so we can get a lot of troubles by eating such contaminated foods. And interesting that in some cases, we cannot remove the presence of such mycotoxin even through the thermal treatment. But during the storage, we should precisely control the temperature, humidity, duration of the exposure of some products to the presence of fungi, and of course to use the antifungals. Which type of antifungals? So that is the main idea of my lecture. So you can see here which type of different foods can be contaminated by the fungi. So you can see that a lot of grains in dry way, even nuts, a lot of trouble, seeds, and so on, dry fruits especially, can be contaminated by the fungi. But probably you know also about such situation, about the presence of fungal cells on the wet walls. And of course, that is a situation when we have not only the growth, but the synthesis of mycotoxins directly in the same atmosphere of our home where we are living. And so the history is following. Already 40 years ago, the first mycotoxin was isolated from the such cells like Aspergillus flowers. That is why, like abbreviation of the name of these fungi, we name aflatoxin, Aspergillus flowers, the first and the most toxic mycotoxin which we know now. And again and again, I already said that different types of fungal cells can synthesize, provide the synthesis of different mycotoxins. So certain type of fungi can produce certain type of mycotoxin. And so that is this idea of discovering of some types of fungal cells inside of crops can be used for the discovery of this mycotoxin, because you understand that the toxicity of these compounds is high enough in low concentrations. And believe me that there are no good analytical methods which allow us to reveal the presence of mycotoxins in their very toxic concentrations in different types of substrates, I mean foods. It is difficult. And so now that is a task for the analytical chemistry. And antibodies and chromatography and many other approaches are applied, but not all mycotoxins continue to be acceptable for the analytical discrimination from the mixture of other mycotoxins and revealing it. So that is a real problem. And the mechanism of action of aflatoxin, the most toxic compound, is following. So we observe the interaction of this toxin with the guanine in the DNA structure. And so after that, we can observe the interruption of protein synthesis because of we have appearance of messenger RNA. That's it. And after that, we have no renovation of cells. And actually, that means this. And the aflatoxin, look here. So the concentration tolerated daily intake is less than 1 nanogram per kilogram. So how do you think, is it possible to use this mycotoxin as a biological weapon? Yes, without any responsibility, because of that is some kind of natural material, natural thing coming from foods and so on and so on. So we need to be very tentative. We should to provide our safety by the analytical methods, controlling different foods, or by distracting these compounds somehow. So, and you can see here that, of course, we already understand that we can talk about some preferences among the foods for some fungi which can contaminate some substrates. So we already understand that in some certain types of foods, we can discover some certain type of mycotoxins. We do not need to check all the presence of all mycotoxins, for example, in bread or in chocolate or in coffee or in tea or some other mycotoxins. So there are several mycotoxins in this group produced by Fusarium fungi directly outside in the places where we can harvest their crop. And you can see here the three main structure, the structures of the three main mycotoxins. And I would like to draw attention to the fact that it looks like lactone containing molecules. It means that actually in nature we have lactonases, enzymes which can disrupt such structures, and we can use them to fight against such mycotoxins. And probably you know that lactone disrupting enzymes can be synthesized by bacteria. And so it is possible to think about the application of such enzyme for the hydrolysis of such mycotoxins. But zearalenone is not so dangerous as compared to aflatoxin, but it mimics the body's production of estrogen, female hormone. And that is a problem. You know, there are a lot of zearalenone in the beer. Yeah, and that is why those persons who would like to drink beer, time to time convert to some female-like person. Yes. So, yes, because of the presence of such mycotoxins imitates the appearance of female hormone in the male body. That is why talking about. And in case of two other three-headed cells, we can get other problems with a reproductive system, but already for the female, because increased concentration of female hormones is also not good situation. And concerning one another, toxin like humanizing B1, we are talking about absolutely 100% confirmed development of esophageal cancer in humans. And that is a problem. And the presence of this mycotoxin was discovered in rice, in hazelnuts, in pepper, and cheese. So after this information for myself, I decided not to eat the green cheese at all because of I do not know about the presence of mycotoxin in these some special green fungal contaminated cheeses. So I do not like the situation, but the people from France, they guarantee that there are no any mycotoxins inside of such types of cheese. Okay, so and I already said that aflatoxin coming from the aspergillus fungal cells, so are very dangerous. But you know, because of the special structure of aflatoxins, it appeared that under the ultraviolet light, it is possible to discover the presence of such mycotoxins directly on the surface of grains, because of some of them give us blue fluorescence and others green fluorescence. So for this purpose, when we have a lot of such mycotoxins, not in nanograms, but much higher concentration, we certainly can distinguish and understand the problem. But aflatoxin, B1, that is strong cancerogen and definitely linked to the cancer in animals. It was already many times confirmed in many countries in Africa and Asia. So that is the result of deep investigations. And first of all, liver is the main center of such trouble. And penicillin producing famous antibiotics, which are widely used in our practice. So they also produce two main mycotoxins, ochratoxin and citrinin. And the problem is following. They are neurotoxins. So they work with our nervous system, and that is why in some cases we have not only the toxic effect on the liver, but also with our nervous system. Moreover, in some cases, ochratoxin reduces the concentration of albumin in our blood. And sometimes we do not understand what happened with our health because we have some troubles like with cold feeling. But that is a result of acceptance of some food with the presence of such liquid. I would like to draw attention to the chocolate and dry fruits. So that is that are the main sources where you can find the presence of ochratoxin A. So chocolate should be eaten without any additives, like some corns inside of or raisins and so. Pure native chocolate, that is a good product. And ergot poisoning. In Russian, sporanya. Probably you know about the presence of such dark grains inside of other types of grains, which you usually apply for your breakfast, like barley, oats, and so on. So be attentive, because that is also a source of ergot, mycotoxin, and a result of here you can see the dermal allergy, especially especially that is important for children, because barley and oats we use for the child breakfast also. But what to do? First of all, to avoid contaminated products, to test, to dilute. Do you know how dilute? To mix contaminated grains with non-contaminated. Usually the producers do. And so cleaning, drying first of all, to reduce the concentration of moisture, or adding some antifungal. Organic acid prevent mold growth, but we can use only sometimes lactic acid or succinic acid to prevent the development of some fungal cells. We cannot add acetic acid, because of we are talking about the foods and their quality. So what we can say about the possible removal of the mycotoxins? So there are several methods. First of all, physical separation. If we can see some contaminated seed, we will separate, and after that, dilute with other non-contaminated grains. So with the flotation, because the density of the grains will allow us to separate contaminated grains. They will always will be on the surface of the water. So we can try to wash some grains, for example, with the water to dilute, to remove some mycotoxins from the surface, for example, of rice. But in some cases, it doesn't work, you already understand, because the mycotoxin penetrate inside of the bulk of mass and contaminated in general. So we can try to remove the mycotoxin by solvent extraction. And do you know what we need to do? To use anhydrous ammonia. Do you know something about the smell of this solvent? So, and it should be done for 2 weeks. What will be with the grains and foods with their quality after that? But that is some kind of result of scientific investigation. So we can try to inactivate these mycotoxins by the cooking or thermal treatment. So gamma radiation does not work. Photochemical reaction doesn't. So chemical methods, you can see a lot of results of investigation where different reagents were tried for the inactivation of mycotoxins. Even ozone doesn't. So, but biological methods coming from the meat, so they look very attractive. And I would like to jump a little bit through this slides. So cooking generally does not destroy mycotoxins. Only, for example, for dawn, it can work, but not for the aflatoxin. For some fuminism, we can get the appearance of shifts bases with some reducing sugars, for example, with the fructose, if we have inside of treated products. But even such modified mycotoxin still have some toxicity. Sorbents. Okay, sorbents probably can help us because we can add some sorbents into our foods or into feed for different animals. And we, some scientists who started to work with such sorbents considered that it is possible to completely remove the mycotoxins from the feed for animals. And here you can see different types of the sorbents which were tried for these purposes. But of course, you understand that we have no chance to add more than 2% to general mass of feed for animals of these sorbents. That's a reality because that is a forbidden. So only 20 grams per kilogram of some grains using like a feed for animals we can use. But finally, you can see that no more than 60% of initially present mycotoxins in some feed we can remove from this general mass of grains and so on and so on. But you understand that we can have absorbance, but after that we will have the desorption of these mycotoxins in our gastrointestinal, not now, but in the gastrointestinal tract of the animal. And so the result finally will be negative. And so moreover, we will get the absorption of some nutritional components from the feed, as well as vitamins. And so we decrease not only the concentration of mycotoxins in the food, but we will decrease the vitamin supplementation. So that is not. And what about the enzymes? Enzymes look very attractive approach to the destruction of mycotoxins because of they have high specificity of action. Moreover, we can take them from the nature. They have no their self-toxicity. They can act not in the stoichiometric reactions, but they can work like bioactives of degradable protein. And in this case, we have no nutritional losses. So if you will look through, if you will go to the internet and you look through the information about the different enzymes which can be applied for the destruction of different mycotoxins, you will see same results as I saw several years ago. So each type of enzyme can be applied against some certain mycotoxin. There are no some universal solutions. And moreover, in some cases, you can see, for example, we can provide the hydrolysis of 3 milligrams of some compound. In other case, in 10 power less, but for the same period of time, for 1 hour. It is quick enough reaction, so each of shown here, but you can see in some cases, we can get huge amounts of hydrolyzed mycotoxins. In others, very low concentrations. It means that we can use the enzyme to destruct some mycotoxins with high enough yield and efficiency, but in some cases, the enzymes are not productive by them. So 2 years ago, I forced my colleagues from my laboratory to find out different types of sources where we can find out some enzymes which can we use in huge amounts and they will be cheap for the treatment of mycotoxins. I understood if we have so low velocities of the chemical reaction, so we can improve the situation by increasing the concentration of enzyme in their treatment. I mean, in the treatments of mycotoxins. And you can see here the phylogenetic trees for different type of enzymes which can destruct, for example, humanidin, DON, deoxynivanillin, valine, no, and so on. And we classified some enzymes which we found out due to the use of BLAST program into the classes of different enzymes, and it appeared that only two classes, oxidoreductases and hydrolases, can be used effectively for the destruction of mycotoxins. But interesting, in parallel to our investigations, we observed the appearance of new publications coming our colleagues, first of all, from China, and they tried to combine different types of enzymes, for example, two enzymes, trying to find out some kind of universal solution. So if you use some not complex but mixture of enzymes which have different substrate specificity of action, you can increase your success in the treatment. And they try to do that, but you know, they have no success, unfortunately, because they have some decreased results in the immunity of animals, their digestion activity, and so on and so on. Why? Because of they decided to mix their enzymes by their own wishes, without any scientific base. And now we certainly understand that the degradation of the mixture of mycotoxins should be, first of all, clearly analyzed by the use of bioinformation sources, because we need to understand, do we have some interaction between the enzyme, not with their substrate in such mixtures? So that is a very important situation. Moreover, we can predict the best variants and effective variants of such enzymatic mixtures by the analyzing different places or sites in the structures of these mycotoxins, and not only mycotoxins, but other toxins, for the action of enzymes. And we did that. So complicated picture, but that is the result for different types of characteristics which were done in my laboratory with the different type of mycotoxins, with the different type of enzymes, and we analyze the possible entrance of these mycotoxins in the active sites of enzymes under the certain type of angle. So, and finally, we found out, interesting, but same enzyme like we used for the destruction of organophosphorus compound appeared to be a good candidate for the destruction of several three different type of mycotoxins during for 1 hour. Interesting, because of the presence of lactone structure, lactone-like structure inside of the mycotoxin. So it is possible to stabilize these enzymes before the mixing and introduction into the sources containing different types of mycotoxins. But it is necessary to understand at which type of pH it will be better to stabilize them. It is also can be done by the informational method, so in silico. And here you already can see the some experiments in vitro, which we made after our bioinformatic or in silico work. And we understand that by using the cultural lines of some cells, we can obtain good results with the removing of mycotoxins. And finally, we already checked the obtained mixtures with the animals. And you can see here the bad results, I mean, with the contaminated by the mycotoxins, with the mixture of mycotoxins, because we always in our life have contact with the mixtures of mycotoxins. And so here you can see the blood parameters or characteristics with the enzyme. Sometimes they're even better without any enzymes as compared to absolutely healthy animals. So enzymes work. And a few words, it is possible to measure the concentration of different mycotoxins by using bioluminescent bacterial cells, because bioluminescence can go down when these cells are in contact with mycotoxins. And we can check different types of mycotoxins with, for example, immobilized cells, bioluminescent cells, widely used as a criterion for the estimation of toxicity. And moreover, it is possible to organize the detection of these mycotoxins not during the half an hour, as usually recommended. It is usually recommended by the producers of the bioluminescent cells. For example, photobacteria. Yes, but we use the flow-through analysis system because of during the same time. But when we put the mycotoxins into the flow, we observe the accumulation of these mycotoxins inside of the cells. So we can observe the cumulative effects and the decrease in the bioluminescence, and we can registrate it, and we can observe the appearance of mycotoxins in some water system if we would like to do that. So conclusion is enzyme can be applied for the treatment of mycotoxins. We need in combination of some mycotoxins to provide the complete degradation of all mycotoxins which we have in mixture. And of course, we need in some various stable of these enzymes to store them, to use them for a long period of time. Thank you.
Mhm. So, раз. Okay. Okay. So, good evening, everybody. It's a great pleasure to be a part of today's event. Let me introduce myself. My name is Roman Goryachev. I represent the Federal Environmental Operator. I'm a head of a group of analytics. And today, I'll be glad to tell you a little bit about the hazardous waste management system in Russia. So, but before we start, let me tell you about like so-called vocabulary. There are five types of classes of waste in Russian classification. The class of waste means the damage that could be done to the environment if it was thrown away. So today, when I'm talking about wastes, I mean only the first and the second class of hazardous waste. So the second point, I'm going to tell you about our digital system that we created that my colleagues will further show you after the presentation. So it's called Federal State Information System for accounting and control of waste management of first and second classes, but I'm gonna call it digital system or just system. So now we're ready to begin. Uh-huh. Uh, and I'll be glad to answer all your questions after the presentation. So, next slide, please. Thank you. The market in the sphere of hazardous waste management has shown its inefficiency. Numerous violations, unauthorized dumps, and abandoned plants. Ineffective management of hazardous waste is a direct threat to our security. The infamous sites of accumulated environmental damage, such as Himprom in Irkutsk region, Krasny Bor in Leningrad region, and many, many other, where the industrial waste from all over the Soviet Union was dumped for decades, are vivid evidence of this. So the difficult situation with industrial waste in Russia has served as a prerequisite for modernization of the waste management system. In fact, formation of a whole new system of such waste management. According to Federal Classification Catalog, there are 487 types of first and second class of wastes, which of them mostly generated by organizations, legal entities. These wastes, there are various types of mercury-containing wastes, lead-containing wastes, and wastes of chemical current sources. Next slide, please. So the state corporation Rosatom has a unique experience in successfully building a unified state system for radioactive waste management. So therefore, the president of the Russian Federation has committed us to carry out a similar work with regard to class 1 and 2. It was necessary to create an effective system of hazard class 1 and 2 waste management. So the federal project infrastructure for hazard class 1 and 2 waste management implemented as a part of the national project ecology. It became the basis for the formation of the new system we're discussing today. I would like to emphasize that within the federal project, we are simultaneously creating an infrastructure that will make it possible to obtain recycling products by processing industrial waste. This will make it possible to significantly save resources through their reuse. And let me tell you that in accordance with the target of strategic documents, by 2030, more than 40% of raw materials used in construction, agriculture, and other sectors of economy should be recycled. Next, please. So the basic decisions have been taken to organize a new system of hazardous waste management. In period of 2019 till 2021, together with the Ministry of Natural Resources and Environment, Rosatom State Corporation, the federal operator, ensured the development of necessary amendments to legislation. Rosatom Enterprise is designed as the federal operator for handling these wastes. which by virtue of state regulation established under the federal law on production and consumption wastes. This is responsible for organizing the safe handling of hazardous waste. Also, the cost of services for federal operator is also subject to state regulation. The cost of services includes the entire waste management cycle, from waste generation to an actual recycling. And Russia's first federal state information system for accounting and control was created. As I already have said, my colleagues will show it to you further. Next, please. So all the information submitted by market participants of waste management will be provided through this digital system. The operator of the system, which is also responsible for its operation and smooth functioning, is also the, all right, we need to make a pause. Clicker. So technical pause. So this was it. A bit quicker. Should I start again, or we can? The previous one. All right. Now we're good. Thank you. So the federal operator is also responsible for a smooth functioning of this beautiful system. This is a digital platform for accounting and control of the entire waste life cycle, as I already have said. And it will help to forecast capacity utilization and optimize logistics. I would like to note once again that this is the first digital ecosystem in the country capable of management the entire chain of operations in the market of hazard waste. Submission of data on all operations with hazardous waste to the system is mandatory both for the federal operator itself and for waste generators, also for waste operators and transportation operators. The system is integrated with other state information systems, which eliminates the need of double data entry and ensures their automatic verifications. So anyone, waste generator or transportation operator, can log in from a tablet, a phone, or a desk computer. All he needs is internet connection and an account on Gosuslugi. It is a platform for public services in Russia. So when logging via Gosuslugi, you can get all the information from state information systems, which has already been entered by any legal entity in advance. It is displayed automatically. Through a personal account in our system, it is possible to obtain information on licenses that have already been issued to participants by Federal Service for Supervision of the Ministry of Natural Resources and Environment, whether there are waste generators, transporters, or waste management facilities. Next slide, please. So there are 4 main types of personal accounts. The account of the waste generator, the waste transporter, the waste operator, and an account of the federal operator. The system has a built-in service that checks all participants for tax non-payments and also shows whether any checks are not currently being carried out on the legal entity of interest. Everyone confirms the convenience of our service from the point of view of automating the processes and procedures involved in checking of reliability of a legal entity that will provide a service. For example, if you are a waste operator, you can be sure that a transporter that coming to collect the waste gave us the best application and has already been verified by the internal verification service. Our system allows real-time monitoring of vehicle movement by using GLONASS. And this our universal protocol supports most of the new Russian-made trackers. After submitting an application for collecting waste by a company waste generator and forming an order, a QR code for TARE is automatically generated in the system. the code contains all necessary information about the container in which the waste is transferred for further transportation. So when loading the waste, the transportation operator reads this QR code and accepts it if all the information is right and verified. In order to work on the digital platform, waste generators need to register in the system and ensure the placement of information on the types of waste generated, sources of generation, locations of storing, and placement limits. If there is an in-house processing facility, information about such a facility shall also be posted. Waste management operators with the necessary license must also register in our system and provide data on their facilities, their capacities, applied technologies, and vehicles. Next slide, please. So let's speak about the system as a digital platform. First of all, it is kind of a one-stop center where all participants provide their information. They make their request if it is a waste generator company, or they can obtain an order. For example, if we're talking about waste operator company. Also, the system provides waste accounting for the formation of mandatory statistical reporting and minimizes inspections by regulatory authorities as the entire life cycle of waste is traceable in the system. The use of system tools for checking the completeness and reliability of information contained, its analysis and processing, including information on the fulfillment of contracts with waste generations concluded in the form of an electronic document, provides a unique integrated tool for high resolution end-to-end traceability of the full life cycle of waste. So, of course, one of the key directions to us is integration with the other information systems of control and supervisory agencies. For example, Federal Service for Supervision of Ministry of Natural Resources and Environment. And at the moment, the exchange of information between us and this federal service throughout our systems allows us to automatically verify data on the facilities entered and registered that have a negative impact on the environment, taking into account the integration, waste transporter or recycler without the appropriate permits will not be able to register in our system. Next. So the next slide schematically presents the state regulation of hazardous waste management. The new system links together waste generators, operators, transporter, federal operator, and interested federal executive authorities. As of March 2022, waste generators that do not have their own facilities for handling wastes must transfer these types of waste to the federal operator by entering into a contract with the federal operator for the waste handling. Then the federal operator will ensure their safe disposal by itself or by concluding contracts with side transport operators or waste management operators. Next slide. Those waste generators that have their own handling facilities have to register on our platform in order to submit all the information about their waste generation, volumes, technologies that they use, and other information that we, in order we can count and control every ton of waste that produced in our country. Next slide, please. So let's pick some numbers. As of yesterday, 87,000 users are registered in the system, representing about 48,000 organizations. That is, the digital platform has actually connected more than 80% hazardous waste management market in the Russian Federation. We consider this as a good result for 1 year and 8 months of our work. So what do we know today? As I already said, 48.6 thousand organizations are registered, including 46.3 thousand waste generators, transportation operators, and waste operators or recyclers. So based on this information, we can see that excuse me, only 30% use recycling technologies, and about 70% have neutralization technologies. While if we talk about technologies at the industrial and technical complexes that we are building right now, 65 of waste will be recycled and 35 will be neutralized. In total, as of today, the federal operator has concluded 38.7 thousand contracts with total weight of 80,000 tons since March 2022. Next slide, please. Of course, it's important to note that before approved waste management facilities in our digital platform, including waste accumulation sites, our specialists carry out a detailed verification of the specified information. With regard to waste accumulation sites, information on the location of the waste, its component composition, the content of waste passports, and information indicated that the facility has a negative impact on the environment. With regard to waste management facilities, the compliance of the declared technologies and wastes with the operator's license is checked. The availability of the state environmental expertise is checked, and the compliance of the declared technology with the parameters established by the environmental expertise. Next slide, please. Operators engaged by the federal operator to provide waste disposal and neutralization services are subsequently subject to on-site technological audits to verify the quality of service provision and integrity in terms of compliance with technological regulation and parameters of the state environmental expertise, availability and serviceability of the equipment used, compliance of the technological process with the requirements of technical and other permitting documentation. For the period of 2022 and the expired period of 2023, about 100 field trips to waste management service facilities were conducted. 84 waste management operators under more than 450 contracts were inspected. If significant violations were identified, there were restrictions imposed until the identified violations were eliminated. And contract with waste operators were terminated if violations weren't eliminated. Next slide, please. So now I'd like to say a few words about how we engaged participants in our digital ecosystem, because at the level of law, there is no liability for not registering in the system and providing information and data. Since March 2022, we have encountered with the low digital maturity of users, with low registration activity of organizations in the system. So what steps we have taken to address these issues? First of all, we concluded cooperation agreements with regional executive authorities, which are involved in informing participants in the market of hazard waste management about the need to register on the digital platform. Second, we organized and hold meetings with the participation of federal and regional legislative and executive authorities, where we discuss improvement of legislative regulation of the industry for handling wastes. Also, we participate as speakers in industry events at the federal and regional levels, answer questions from representatives of specialized organizations. We provide regular training of system users, namely, we conducted more than 160 webinars, during which we showed and explained step by step how to work on the digital platform. Also, we have organized the free 24/7 technical support service for users and initiated amendments to federal legislation, namely administrative liability and fines for violation of the procedure for submitting information for officials, for legal entities, and persons carrying out entrepreneurial activities without forming a legal entity. So I think this is short enough to tell you about our system. If you have any questions, I would like to answer them. And after your questions, you'll have an ability to see the system for yourself. So, is there any questions? Да. Да, сейчас она работает только в рамках Российской Федерации. Смотрите, на данный момент мы работаем только с российскими юридическими лицами. Насколько я знаю, вообще Росатом ведет переговоры с некоторыми странами СНГ на этот счет, но на данный момент пока только это российские юридические лица. Вот буквально когда-то недавно тоже на школе. Today we work only with the Russian legal entities. Maybe Rosatom thinks about working with other countries, but today I can't say that for surely. Yes, please. Oh, okay, yeah. Thank you for your question. Waste op mhm. So, mhm. Okay. So, when I say waste operators, it means recyclers who have handling facilities in order to recycle those wastes. So, waste operator means recycler, but different recyclers have different technologies. As I had, may I? Thank you. As I have said on this slide, these facilities use different technologies. Of course, we also have site operators who have disposal disposal facility also, but we are trying to achieve a greater percent of neutralization and utilization of wastes, because it is more environmental friendly to utilize them in order to have production. After recycling, we get production that can be used as raw materials again. So this technology is better, and we're trying to achieve that. Actually, those waste of I'm talking about, those 487 types of waste, they all can be utilized or neutralized. There is no need to dispose any of them if we have enough capacities, enough capacities and technologies that can recycle them. So we try to get from disposal much far as we can. All right. Any other questions? No, right now, every handling facility that operates today have to conclude a contract with federal operator. They can obtain waste from other countries today. No, they can't. No. right now, no. According to today's legislation, no, unfortunately. But I think in the near future, we will work on that. Thank you for your question. So, some question? No? So, I think I'll invite my colleagues to tell you about the system. And actually, you can come here and look at, and yeah, a bit later. Sorry. Thank you.
Good afternoon. Um, Good afternoon. Today we show you our system, the Federal State Information System, or FSIS, or digital system for short. The system was created within the federal project infrastructure for waste management of the first and second class hazard class of the national project ecology. The system is a digital environmental protection tool for accounting and monitoring the entire life of the waste of the first, second hazard classes. The platform monitors the entire life cycle from the moment of the waste formation to actual disposal. The platform ensures interconnection of market participant within one stop shop from anywhere in Russian Federation. Moreover, it helps keep a logbook of waste generation, ensure waste accounting for the obligatory statistical reporting, sign contracts, and to apply for waste removal in real time, provide rapid e-document exchange, ensure the disposal capacity of operators, optimize the logistics routes of waste management, in particular its collection and transportation. The system is a national development, which has microservices architecture. It is Python-based. The system software was developed using the technology of non-stop server migration. Moreover, it is adapted to national server hardware Elbrus and Baikal. The digital platform has mechanisms of information exchange with other state information systems. Thus, it eliminates the need for double data entry and ensures its automatic verification. You can log into the platform from a tablet, phone, desktop computer. You only need the internet and account on public services of the Russian Federation. When you log in through the unified identification and authentication system of public services, you can get all the information from the state system. All information entered by any legal entity is available automatically in the platform. Via the personal account, you can get information on license issued in system of federal service of for supervision of natural resource. There are many four types of personal digital cabinet of waste collector, waste transporter, waste operator, and of course federal operator. And now you have a unique opportunity to see how it works online.
Physical activity and come up to the platform. Stand up, please. And we'll show you in online how it works. Okay, so here's the starting point of our system. And my colleague will start talking.
Okay. Now the system allows monitoring the movement of a vehicle in real time using the EGTS protocol. It's a standard. The EGTS protocol allows tracking the movement of a vehicle in real time. The universal protocol support most of the new Russian tracker devices. Our platform is a transparent system that allows performing real-time data monitoring. The system is linked between the state and business and waste.
Yeah, so here you can see our vehicle has been driven in real time. So the starting point is number 21, and it goes right through our subject of the Russian Federation. So you can feel free to try, swipe it. Yeah, right. Great. So, and the final point is number 3 here. That's true. Okay, so the next slide will be, pardon me, the final point of all the collection of waste. The point is number 20. Pardon me, number 19. This is the final point where all the waste get. Okay, so the next thing we wanted to show you it is the account of our organization. So here you can see our federal environmental operator, and here you can see everything. And the same account has each organization entered into our platform. So here you can see all the licenses, the places of waste generation. Then you have the waste processing facilities and vehicles. And the next thing are treaties. Yeah, so that's the fullest account we have here. And the last slide is the applications under which we collect all the waste. So we can continue the status. So here we can see the map of Russian Federation and the places of waste generation. And each place of generation has its status. So if it's green, it's approved. If it's orange, it's under check. And if it's red, it's declined. Yeah, so here you can see the map of our country in real time. So we can continue with the recycling facilities. So the same thing here. If it's green, it's okay, and if it's orange, it's on check. So we can go next to the next slide with our analytics. Here is again the map of our country, but it's a bit in different form. So here we can see the analytics of our places of waste generation, and here is the concentration of the amount of places per area. So the biggest amount is in Moscow per meter, so to say, and the least amount is in the north. Yeah, there it is. So the next thing you can see is data considering the waste processing facilities again. And the biggest amount of waste processing facility is in the middle of Russian Federation. Okay, so what do we have here next? Yeah, so here you can see the data of waste and its reports. So we have a special type of menu here. The first thing here is the analytics, the accounts of different organizations, and then here we can see the logbook. The logbook is the greatest thing considering the administration and the management of waste recycling. And here in logbook, each operation with waste is fixated. And the appearance of waste fixated in the logbook. And here you can see the amount of waste fixation in the Russian Federation. So the biggest amount we can see, or we can check in Moscow and in Krasnodar region. So it's pretty young. Questions, feel free to ask them. To the whole information in the platform, just our group and the federal service. Now you will see just your information in the platform. Yeah. Yeah. So the whole information can see only us and our federal service. Yeah. You can see the information considering the result that we observe. The information considering the organizations that have their license is not open yet, and the only entity who has that information is our system, and that's it. And federal operator just see the licenses that our federal service provide us. Yeah, it's logbook. It's filled in 10, it has to be filled in 10 days after the appearance of waste. Yeah. Spike? What do you mean by that? So you mean that the difference is great between the region and Moscow, or what? Mm-hmm. Mm-hmm. Yeah, that's this is analytic just in our federal information system, but it doesn't stand for it to be the truth, because not each entity now has the is entered their information into the system yet, because we try to make it digital, but the whole system in reality isn't digitalized yet. So here is just a middle result of our work, and we are planning to get more. Mm-hmm. Some other alternative. Mm-hmm. Yeah, that's a unique system. For so long, we have that Russian Federation was the first who invented such a system. Yeah. Of course, it's possible, and it helps to build new international ties, and Rosatom any offers, and it's free to and it's free cooperation, right? Of course, of course. Actually, the reason for today's meeting was to share the experience, to share how we do that, and maybe to get the feedback. Yeah, it's of course possible. Yeah, so we can fix it. And if you are an expert, you can just tell my colleague your contacts, and we'll stay in contact them. So, any questions? Mhm. So you mean the cooperation with what? I don't really get. No, you mean the recyclement is free or not, or you mean the use of? Of course, that's free to enter to get your account there, and any person who, pardon me, any legal entity, because we don't work with physical, we don't work with people, with real people, only with companies. And each company that has the first or second has a waste of the first and second has classes. Mhm. Of course, yeah. It's free for any type of entity in our system. So the only thing you have to pay for or to get money for is the recyclement and the handling of waste. Of course, that's it. So, and the whole system was invented due to the administrating and management of waste in the whole Russian Federation. So it can't be paid. We have a special ministry. So, yeah, yeah, yeah. It's just a tool for administrating and monitoring the information, and that's obligatory to enter the information into the system now. But we don't have any right to punish them. Yeah. Yeah, it does.